Hey everyone, we will just wait a few minutes for Carl and others to arrive. Hey Andreas, I think you're muted, which is also very fine. I at least can't hear you, but I mostly wanted to say hi. I don't think we've met.
Oh, my name is Andres. Hi. What's your name?
Peter.
Peter. Oh, you're the moderator. Okay.
Yes, the moderator and the speaker.
Okay. Very good.
Where are you based, Andreas?
I'm in Lithuania, and I started attending, I guess maybe a few sessions ago, and I learned about active inference through Daniel Friedman.
Of course, he's a wonderful person.
Yeah.
I am just, while we're waiting, keeping an eye on the email in case I hear from someone. But I don't think anything has come up. We've just recently switched to Zoom, as you probably know, and that means that there's a little risk that some people haven't used the new link yet. So I'm just making sure everyone knows where we are. It's nice to meet you, Andreas. And while we're waiting, I'm just checking that you can see and hear me properly, that I'm not lagging, because otherwise I would switch to some other network. Good. I see someone has joined who's called MB. Have we met before? I don't feel pressured to.
Hi, yeah, sorry, I was having audio trouble there for a moment.
It's completely okay. I mostly wanted to bid you welcome.
Hi.
Say hi.
I'm also having video trouble. Oh, there we go. Yeah, I've been along for the ride for a few of the meetings here, but I have a different profile name in Zoom, so
Yeah,
it's just
sure.
based on my email. Yeah, I can change it. So yeah.
But what is your name, if you don't mind?
It's Mark Broberg. Yes.
Yes, for sure. Hi, Mark.
So I've been to a few of the meetings, and I presented at one back in January, and we'll be in September. I'm in California here on the West Coast. So I'm a physical therapist and aspiring to learn the science here. So I think that modeling will be very helpful to learn here.
It's I do remember your name.
Okay.
Of course, as it shows up in our systems, of course. When
Okay, good. So, I'm not a troll here.
no, not at all. I was mostly trying to make sure to connect your face to the name. And
Right. Thank you.
Okay, nice to see you, Mark. So I hope it will be a little bit useful for you. We'll see.
Yeah, I think so. We just submitted to the IWAI in Montreal, and one of the reviewers gave us the feedback because it's more of a theoretical, clinical model. And they said, well, if you could model this, and show the computations, that would bolster your work. So I thought, okay, I think that if I learn what's going on here today. Maybe that'll be helpful.
I'm at least going to also give a little overview of the technicalities, so that might be of interest at least.
Great.
And nice
Perfect.
to have you.
Looking forward to it. Thank you.
And I can see that Carl is here also. Hi, Carl.
Hello there.
Hi. Okay, so then I think it is time to start. Today I'm in the somewhat awkward, but also somewhat pleasant position of being the chair and the speaker, which means I'll just keep the timing. I think, Carl, I can't ask anyone to clap at me, so I'll skip that part. But apart from that, I'll do the rest.
Yeah, I'll do the clapping then. All right.
Okay, sure. I could find no way where it was not rude and the opposite of humble to ask an audience to clap at oneself. Okay. So then I will get started. I will also introduce myself and what I'll talk about in a second. I'm sharing my screen and I will just check that you can now all see my slides and that it says something with ActiveInference.jl. Is that correct? I can't see anyone while I'm sharing, so
Yeah,
so I'm
no, we can see that. Yeah.
Perfect. Thank you, Carl. All right. So today I am presenting on behalf of my team, including Sam and Jonathan, who are here in the audience, and others, which I will introduce in a moment, on the Julia implementation of the Active Inference package that we have been working on. And in particular, I'm going to present on our plans for where we want to take it in order to get feedback from the community and make sure that that's a decent place to want to take it, so that we have the opportunity to change course before and not after we've restructured the package. And I'll talk more about that in a second, but we want to facilitate at least going beyond discrete POMDP generative models for those who would like that. And also we're focusing specifically on trying to make active inference easier to use and more accessible, and also making a tool that will work with the wide range of different use cases that the framework has. Yes. So today I'll just start with reminding us of the basics in active inference. The purpose here will be partly just to make sure we're all aligned, because I'll build on this in the second part, but also to make sure that if there's something I'm getting wrong, I get corrected now before we build something wrong into the package. And also give a little overview of the applications I know of, at least for active inference, and that the software package should be able to accommodate. And then we have a conceptual structure for the package that we want to build it around to make it modular, and also some implementation design that we hope the audience here will share their thoughts on and help us make the package as useful as possible for the community in the future. Yeah. And so like I said, we want feedback from the community. I'm also gonna have some boxes like this as we go with some very concrete questions, and I might embarrass myself a little bit from time to time with these questions because I'm not yet fully versed in all aspects of the literature, and so some of them are clarification questions on parts of the literature that now matter, because we're gonna restructure the package, and we want to avoid doing that many times. But of course, the point is also to catch errors and confusions on my part, and to make sure that there's not some important or useful features that we've overlooked, because we want to make the package so that it could, at least in principle, accommodate the at least primary features and tools that we need. And finally, we're gonna give some naming. So the attempt is to make the structure intuitive for users, and for that, some feedback on the naming of the different components would also be nice. So we're going to try and decompose active inference a little bit into some modular parts that a user can then combine and what those parts should be called, etc., is also something that would be nice to be aligned on. So that means today is a bit more of a feedback session, and it means I won't impress you with exciting new results or anything like that. And I hope that that's okay. Finally, I think and this also for those who might in the future be watching this recorded, we of course also want to make sure that the package is easy to use and to develop and contribute to for the active inference community. And so it's nice to keep that in mind also, that for anyone who now or later wants to be involved, that we want to make it now so that it's easy as possible. All right. Finally, I just want to introduce the team that's been working on this package so far. So Sam and Jonathan are the two students who has done most of the actual implementation of the package under my supervision, and who are brilliant and motivated young students. Third student Dominic has just joined the ranks and is now learning the ropes, so he can also help develop the package and use it in the future. Then we've been collaborating with John Boyk from Versus, who has been implementing sophisticated inference in the package, but who's also been part of developing, or at least discussing what we're proposing today. Of course, there's me. So I'm a PhD student, almost finished, hopefully finishing this fall, or that's very likely indeed, at Aarhus University, where Sam, Jonathan, and Dominic are students. Although Sam, Jonathan, and I will be moving to Zurich in the late fall to the TNU at the ETH. So that's the group in computational psychiatry where Klaas Stefan works. Finally, Chris Mathis is my primary PhD supervisor, and he's been supervising this part of the project too. And then I'm mentioning the TNU, so the Translational Neuromodeling Unit at the ETH, here also because they're hosting our software, and it's kind of conceptualized also in the context of the other software tools that they're developing. Okay, so the basics of active inference. And to remind us, the point here is just to remind everyone and align on what we mean and what things are called, but also to check that I understand everything correctly, so that I can correct it if I do not. So, of course, active inference consists of using variational Bayesian inference to form beliefs about the environment, and then selecting actions by minimizing an expected free energy in the future. And both of these components are based on a generative model. So currently in the literature, people usually use fully discrete, partially observable Markov decision processes. I've looked this up a little bit, and of course, a partially observable Markov decision process doesn't have to be discrete, but we usually use those, and they also there are some reasons for that. But notably, they can be discrete or continuous, both in terms of the actions that they take, the observations that they produce, and the states that change within them. Yes, and notably because, as far as I understand, because we're minimizing an expected free energy in the future, we are licensed to call this inference, so the action part also being called inference. But I want to just, so that's the first of the little clarification questions, make sure, especially because I haven't worked with the derivations of the expected free energy myself, I only used it primarily, just to make sure what the official reason is that the expected free energy can be interpreted as a free energy, and therefore that the minimization of it can be interpreted as inference. And also just remind us of the different types of Bayesian inference that I know about. So of course you can do analytic or exact Bayes, and that's usually intractable, but not always. So users of pymdp or of these POMDP models might know that the parameter inference component here, where you learn the parameters of the matrices, is actually, as far as I understand, at least analytic. So we don't need to approximate it. And of course, there's variational Bayes, where we choose a posterior that has the lowest variational free energy, and that can be shown then to be the posterior that approximates the true posterior the best. And then we have what we want. Notably, I think often the primary, let's say, not necessarily downside, but at least what's sometimes called the downside here is we have to assume a shape of the posterior in order to do optimization on its sufficient statistics, or the parameters of the posterior distribution, when we minimize the free energy. There's also sampling approximations, where you essentially find clever ways to draw random samples from the distribution in a way that the proportion of sample of times a given parameter is sampled is proportionate to the to how probable it is in the probability distribution of the posterior. And there are many types here, some that use gradients to optimize this process, some that do not, etc. Notably, this is much slower. The advantage is you don't have to assume the shape of the posterior. There's still many ways it can go wrong, and there's kind of a discussion ongoing if it's less useful for example, Bayesian model comparison, where you have to fight much harder in sampling to find a decent approximation of the model evidence. And finally, there are also these neural approximation methods where you basically train a deep neural network of some specification to produce the posterior, or at least a point estimate, given the observations. So you can amortize the whole or parts of the Bayesian inference, and that has some advantages, like you can do it fast, so that's useful sometimes when the other methods shown here are either intractable or impossible. But of course, using a deep neural network like this, as always, has many downsides too. I won't focus on that too much here. Just note that so as I'm under the, I have the understanding that that's what we mean with amortized inference, that we use, for example, neural approximations. But I also have sometimes spoken to people from other fields who use the term somewhat differently. So I just wanted to check here if that's what we normally mean with amortization in active inference, or if I got that terminology incorrect. Yeah, I should mention that my background is in cognitive modeling and computational psychiatry primarily, not in machine learning. And so that shapes a little bit where my expertise lies, and that will become apparent. Finally, I'm just reminding us of sophisticated inference, here conceptualized in a graph to make it easier to see. So we might have some set of actions, and in this simple case, just two possible actions, and we want to choose a policy, so a set of actions into the future. Normally we can choose a set of actions, simulate forward what kind of state the world would be in, and then look at how close it is to our desired state, and so on. But in sophisticated inference, we want to also simulate our own belief updates in the future. And so in a graph, the way we do that is we have two actions, and then for each action we then have a set of possible observations we would get if we chose that action, and there's going to be probability assigned to each possible observation. And so that's our predictive posterior given that action. And often we prune this tree to make it not become too large, so we cut off observations that are too unlikely, so we don't have to consider them. And then for each observation, we run our perceptual inference process in the future to know what beliefs we would then have. And then we, with these new beliefs, go again and say what then at the next time step, if we chose another action, what would happen? And then we can keep building like this. Yes. And notably, at least as far as I understand, so I haven't had my fingers deep in the sophisticated inference code yet, but we then weigh each, basically, let's say our actions were A1 and then A2. Then there's two A2s, so two paths through this tree that fits that policy, that set of actions. And we then calculate expected free energies for each, and then we weigh them by the probability of these two observations when we calculate the final expected free energy of that policy. Yeah, good. Then I'll remind us of the different applications of active inference. So to my mind, at least, there are three fields or three ways of using active inference as a formal model. So there's also, you can also just use it theoretically, or you can have theories that there's going to be some kind of prediction error signals in the brain and look for them, but using active inference just as a non-formal conceptual framework, which I'm not caring about right now. So using it as a formal model, so as a concrete mathematical and computational model, I know of three ways to use it. That's theoretical modeling, machine learning, and applied cognitive modeling. And I'll go through them now, but just keep in mind that I would like to double check whether everyone here agrees that this is a good characterization of the ways people use active inference, because we're trying to make sure the software can accommodate either of the three. Most softwares are focused on one or two, and we want to try and keep the breadth here. So in theoretical modeling, you usually use simulation and sometimes formal proof to investigate how an active inference process would unfold given some environment. And there can be one or there can be more active inference agents. For this, if you have many, it's agent-based simulation, but it's the same principle. And I'm just noting the Daphne and colleagues paper here, where there's references in the end, where they use formal proof specifically for two active inference agents playing the prisoner's dilemma. So you don't have to simulate, although simulation is very common. And here the goal is often to demonstrate that some phenomenon, for example, hallucinations or loss aversion or some kind of behavioral or cognitive phenomenon, can be implemented or described as active inference. This can be kind of at the belief or computational level, or it can be at a neuron level too, where you can show that some P300 shows up in your theoretical simulations. Often then you need some kind of link between the belief updating level and the neuronal level. It can also just be to investigate what would happen in a given scenario, and that's specifically relevant for kind of emergent dynamics. So for example, when you have many agents, do they form groups or not? And how does that, or fish that swim together, one of Conor Heitz's brilliant papers, how do their behavior depend on the priors and so on? And you see that in some parameter spaces they will form a group, and in others they will disperse. And of course here we need interpretability, we need manipulability, so the ability to set these things very precisely to see what happens. And we also want to be able to have intermediate values. So for example, in sophisticated inference, you can set it up so that you can extract the, for example, expected free energies over each point in the graph I showed before, which can be nice for this purpose also, in case you have theories where it depends not just on the final expected free energy for a policy, but also what parts of it, for example, how it relates to neuronal dynamics and so on. In machine learning, of course, the goal is to deploy the software in real-life use cases. And of course, we want to generate efficacious behavior, so behavior that does what we want it to do. Saves people from burning houses, recognizes faces, whatever. But we often use simulation to test or demonstrate approaches. And of course, machine learning is the field where I'm the least well-versed, so I'm going to stay at this very abstract level, except to say that here speed is often really important, and so is efficacy. So we want the tools we build to do the right thing and do it with minimal computational cost, because often you don't have much time, you don't have many computational resources. And we sometimes need interpretability, but perhaps primarily for debugging. So as long as the machine works as it does, you don't need it so much. But if you need to find out why it goes wrong or to fine-tune it, we need some interpretability. And finally, in applied cognitive modeling, as I'm calling it now, which is what's used in, for example, computational psychiatry, the goal is to reverse engineer the behavior generation process of some system of interest. And when we're modeling it as active inference, that corresponds to finding out what was the generative model that this system had, but also other features, perhaps, of its perceptual inference process or the active inference part. We might ask something like, did this system use sophisticated inference or not? And of course, for example, in computational psychiatry, the system of interest is usually a human being, and we might be interested in people with and without a clinical diagnosis, but you can also use this method for animals, organoids in principle, or even simulated systems. And I don't necessarily like putting my own references here, but we did that, I think. And I don't think most people are necessarily familiar with that being a possibility. So you simulate a bunch of little agents, you get a big agent out of it, and importantly, you don't know the generative model of that group, and so you can use applied cognitive modeling to try and make inference about it. You can do this to test formalized hypotheses with Bayesian model comparison. So you have multiple models, you see which one best fit the data. In the same fashion that the physicists, as far as I understand, try to decide how much dark matter there is in the universe, we might also ask, do, let's say, primates have sophisticated inference, or what's the temporal horizon of primates? But we might also often want to relate the things, for example, parameters that we infer about the system to other things, often clinical variables, like whether you have a diagnosis or some treatment. You might ask, what does taking psychedelics do to your priors, but which priors also, for example. Or you might relate the results of the inference to your physiological measurements. So, for example, which activity in which parts of the brain correlate with high prediction errors is a classic question. But it could also be pupil dilation, heart rate, etc. And here we need interpretability. We need universality, because often there is a wide range of theories that one might come up with, and the tools should be able to handle all those. And we really need precision. That's why people in this field often use MCMC approximations, because they were worried that having to assume the posterior shape of the posterior is problematic. It isn't always, but people are often happy to spend much longer to get the results here. And we also need to be able to extract intermediate values. For example, if you want to correlate brain activity with, let's say, the prediction errors, or also components of the action selection process. Yeah, and they can of course be combined. So we've already seen that with the theoretical simulation that uses cognitive modeling to be understood. But you can also do cognitive modeling, get out parameter values, and use them in a subsequent simulation. And there's many other, I'm sure. Yes, so I hope this is a decent structuring of the field, because they have different requirements, and we want to try and allow all three. Okay, now to the package itself. So first, just briefly, I just wanted to say where it is right now. It's currently part of the TAPAS ecosystem, so that's part of the TNU. That's the ecosystem that the TNU has made, primarily for computational psychiatry. And here we see the legacy of me and the rest of the group, except for John, primarily being into applied cognitive modeling as a use case. I think that's a decent place to have it, and at least is where it is currently. So we'll be working closely with that group onwards. And so far, the focus has been on applied cognitive modeling and a little bit of theoretical simulation, and on fully discrete POMDP models, as we've described before, just like pymdp and some of the other standard softwares that exist. And notably, we haven't yet, although this process is starting now, optimized the package, so Julia can be pretty fast. But currently, it's not as fast as some of the alternatives. At least not as the JAX implementations of pymdp and some of these things. But we'll be working on that. And we have, at least currently in my mind, three primary aims. So one is that we want one tool that can accommodate all three applications, which means that if someone makes an interesting new development in machine learning that can solve some task, that's immediately available to the cognitive modelers and the theoretical simulators, so that a cognitive modeler might then also be able to model a kind of task that can now be solved. Someone develops sophisticated inference and implements it. Now we can ask, do primates have sophisticated inference? Because if you have different tools, you have to kind of re-implement the same thing many, many times. We also want to lower the technical and conceptual barrier to active inference. At least from a sense I have from discussing with people outside the field, but also within the field, is that it's somewhat notoriously hard to get into, which can foster both confusion, but also, I think, some enmity. And so people feel left out, or both overexcited and over annoyed, I would say. And so simplifying at least conceptually or from the user interface, simplifying things, I hope can help deflate a little bit. I've heard you say this a lot, Carl, deflationary approaches, which can avoid these kinds of things, but also, of course, in general, just to make the framework be used more broadly. So I know, for example, in cognitive modeling, there are many people who would like to use active inference models, but find them too difficult to use. These are, of course, particularly people trained in experimental psychology and neurobiology, to whom the barrier of having to understand the hand-coded variational inference and actions error, all of this is difficult, especially when many of the terminology and so on feel foreign. And finally, we really want to make a tool that the community around active inference can easily extend or adapt, so that it's not just a little team like us that can use it, but maybe democratize it a little bit in order to also speed up the progress in the field. And for that, of course, we need it to be readable and easily editable. Yes, just checking. There might be other important things that I'm forgetting. So I'm leaving these little questions up just so that the audience can, if they have an answer to them, write it down and then they can tell me later. Or maybe if we go through the slides later or something, that's good stopping points just to check. So we want to make the code able to handle all three use cases. That includes being able to do Bayesian inference on the active inference process as is done in cognitive modeling. So that's why we're in Julia, because that allows that very nicely. We want to be able to model many kinds of models, so not just the POMDPs, but also the many other types of model that exists. We also have, and I'll show that in a second, a suggestion for a modular structure where you can combine, sophisticated inference with many types of generative models, etc. I want it to be easy to extend, also with custom components, but also with external tools, so we can rely on software that makes this easier for us. We want it to be easy to use and easy to develop for the rest of the community. We want it to be to allow for interpretability, because at least 2 of the use cases really need this. So there should be ways to extract, for example, the full graph in the sophisticated inference of at which time points the expected free energies are high and low in your imagined future. But we also need it, of course, to be fast and to be memory efficient. And sometimes the interpretability and the efficiency are at odds. So the hope is to kind of have not necessarily a debugging mode, but an interpretable mode where you are saving everything as you go so that you can read it out, but you can also not turn that on, and so things can be faster. We also need speed in cognitive modeling sometimes, because especially if you use sampling, it can take a long time to fit a model, long enough that it's actually a downside. Okay, I hope everything's good so far. So if anyone has clarification questions, they should feel free to ask them as we go. Otherwise, there'll be time in the end to discuss. Yes, and I'll maybe make a little time for that in a second. And again, maybe there's some ideas here that's missing. Yes, finally, just a note on why we're in Julia at all as a programming language. So, I mean, people can fight for ages about what programming language is best, and I don't have a strong opinion necessarily on that. I found it a very pleasant experience to use. I also know that it can feel more familiar to people coming from MATLAB. But I think the main aim of Julia, as opposed to something like Rust or C or some of these very fast languages, is to be pretty fast, about as fast as Rust, for example, but while being very easy to use. Because often we have this, so for example, when you code in Python, you run into what some people call the two-body problem, where you need to implement your actual things in some underlying framework. And in Python, people often use JAX, but there are others. And then they have a Python wrapper, so they can code in it from Python. And that works very fine as long as you're not trying to develop and extend the models, for example. So Julia is also auto-differentiable, which means that any Julia code can be differentiated through, and if it can be differentiated through, it can be used for Bayesian inference. And that's the primary reason I'm using it, because it means you can use any of the tools that already exist in Julia for your cognitive modeling in this specific case. I'll return to this. So could have been other languages, but I think it fits this focus pretty well, that we want it to be easy to use, easy to contribute to, easy to edit, to avoid only a small subset of elite programmers to be able to develop the tools. And I know some of the PymDP developers have just been so busy with the many requests they get for tools. So the more we can make it easy to add to it, the less the less busy I will be, which is also a good thing. Okay. Yes, good. I'm going through this a bit fast, but I hope that's fine. I want to make sure we have time to discuss afterwards. Yes, so now we will propose a conceptual structure, so decomposition maybe of the active inference process that is intended to be modular, so that people can switch out parts of it without having to touch the other parts. And this is perhaps the place where I'm the most eager for inputs, because it's the place where we might be the most wrong. But we intend, if it's a good structure, we intend to use this as kind of the skeleton structure within the package. And so you can add and remove different components, but that's kind of the underlying structure. And so we are inspired by the Donizeau et al. Papers from 2010. You might remember those, Carl, where this is in the context of computational psychiatry, however, but that's why I know them, but we're also only inspired by them, but where Donizeau points out that in most, probably not all, but most of the cognitive models in general out there, there are two components: a perceptual model, he calls it, and a response model, where the perceptual model is the model where the agent makes sense of the environment, and the response model is the component where the agent chooses its actions based on what it thinks the environment is like. And so this fits very neatly into many of the Bayesian mind models, where you use Bayesian inference for the perceptual model, and then you choose some other kind of response model. But it also fits with reinforcement learning, where you essentially just use reinforcement learning instead of Bayesian inference as your perceptual model, and then for response model, you do something else. And the sense was that it also fits actually active inference pretty well, because we have first, and it is usually first, a perceptual model where we update beliefs about the environment, states and parameters of the environment given some observations. And then we have another component where we choose our actions by minimizing the expected free energy. And so I'm not going to call it response model, because response implies it's very passive, and it implies you get a stimulus and you respond to it. And of course, active inference and machine learning and many other fields, that only works in some types of experimental neuroscience and psychology. But we think this overall splitting might actually be useful. Crucially, because one response model in an active inference setting, let's say a sophisticated inference tree search, can be used with many different perceptual models. And I'll get back to that in a second. So we propose this structure into 4 parts, where 2 of them are perhaps conceivable as parts of one thing. Indeed, because as opposed to Donizeau's very broad character, in active inference, there's always a generative model environment. So we have a generative model, and the generative whether it is parameter learning or state inference or model structure learning. So I'm changing my beliefs about what the environment is like. The difference between these 3, of course, is more, so parameter learning and so on is primarily a time scale. Yeah, I'll get back to that in a second. Prediction would perhaps also something you just call it, so that's the predictive posterior, which when you form beliefs about what is going to happen based on my actions. and based on my current beliefs about the environment. And then we have an action process. I'm just calling it action for now, which uses the perception and prediction processes above to choose its actions. And I'll try and demonstrate that. Yeah. Notably, I've made a little circle line here from perception to prediction in order to say that prediction doesn't use perception, the perception function call, for example, but it does use the beliefs about the environment that come out as a consequence of the perception. So the generative model, one thing is the formal model itself, and another is its concrete implementation. The distinction becomes a bit relevant in a second, because you can implement the same generative model in different frameworks. And dependent on then the implementation of the generative model, you can do perception on it in different ways. You can even do variational Bayesian inference in different ways with the same generative model. So maybe you can also do prediction in different ways. Notably, this prediction, so this is what creates the expected states and expected observations given some set of actions. And yes, all action has to do is to then return a posterior over the action at the next time step. So that's ultimately where you end. You need a distribution over what action you're going to take now. But that's often done by first calculating a posterior over policies and then marginalizing them in. Yeah. So this is the structure we want feedback on, and I'll say a little bit more about it. But here, just to revisit the sophisticated inference, which we've seen already. Notably, what's done here to calculate the probability of these two observations would be the prediction step here. So there, the expected probability for the observations, so the predicted posterior over observations, for example. And in the sophisticated inference process, you should be able to just plug out a prediction function without as being kind of agnostic or being fully agnostic to how it actually works and which generative model it's based on, as long as you get out the probabilities of the probabilities of the states observations in this case. You also need states for calculating expected free energy. And similarly, not in expected free energy, but specifically in sophisticated inference, no, not in normal active inference, but specifically in sophisticated active inference, you run the perception call, the perception process, perception function, if you will, from here in the future. And again, the sophisticated inference tree search itself can actually be, at least that's the claim, agnostic to what kind of generative model you're using and what kind of perceptual inference process you're using, whether you're using analytic Bayes or a variational gradient descent Bayes or some other tool. And of course, the same is the case with vanilla or normal active inference, that you just don't use the perception function in the future. And as far as I know, these are the two things you would need where you can rely on something else entirely. Yeah. So I have three questions here. I'll start from the right. One is, when we say active inference, I'm used to using it to refer to the whole structure here. So having a generative model, using variational Bayesian inference as perception, using some prediction, and using those to minimize an expected free energy. But of course, when I was sitting and trying to make up names, you clearly have a perceptual inference part, which is the two in the middle, and an active inference part, I suppose, in the end. And when we're making documentation and so on, I want to make these things very clear to avoid confusion. So now I'm kind of asking what the suggestion is, that how we want to use this terminology concretely. And in general, if naming for these four components, and or if there are other components that should be there. And finally, because basically we're going to put different things different places. So the structure of the matrices clearly depend in the generative model, specifically even in the formal model, if you are doing a discrete POMDP, while the optimization scheme used in variational inference clearly belongs in the perception part. And the cutoff for which observations to ignore based on the probability in sophisticated inference clearly belong in the action part. And so we can structure it like this so that when users specify these different settings, they specify them in these structures separately. And so they can kind of do that without caring about the rest. Because currently in many of the packages, you just have a long list of all the specifications unstructured. But so one thing I have been discussing a little bit where belongs is current beliefs about the environment and priors. And the reason I bring this up is because I'm used to thinking that the current beliefs about the environment are in your perception, not in your generative model. So the generative model is, I suppose, so to speak, a model of how the world works in general. And then you have some beliefs about what it's like right now. But of course, priors are usually, in my experience, said to be part of the generative model. And notably, my beliefs about the environment are my priors in the next time step. So the two...
Peter, sorry to disturb you, but it seems like the PowerPoints or the slides, they have gone.
Okay, thank you for saying that. Can you see my screen at all?
No, it's just dark.
Okay, let me try and restart this.
For what it's worth, I can see your screen. I can
And
see
I
that
can
you
see
still
it
have the
too.
model up.
Okay.
It just
The
disappeared from me.
model, yeah.
Well, you've seen these slides already, Jonathan, I think. But I'll stop sharing and start sharing again. Yes. Oh, and I'm not keeping an eye on the waiting room. So if someone else sees someone entering the waiting room, they're welcome to admit them if they're able to. The reason I'm not keeping an eye on the waiting room is because I'm presenting. And I'll finish before too long. Yes. Can you see it now, Jonathan?
No, for some reason I can't, but it's fine. I have the slides.
I can't see it yet either.
Okay.
It disappeared.
Weird.
That's frustrating.
What we can see is double click to enter full screen mode.
Okay. Okay, so it's can you see me though?
We can currently see you, yes.
Good. I'll try one other thing. I'm terribly sorry about this. Okay. Does this help? Do you see the window? No. Okay, trying one more thing. Do you see this? Should be some code and some web page. I'm trying to share my other screen here.
No, we've just got...
not for me.
Oh, that's very annoying. Huh? Okay, with your permission, I'll just briefly leave the meeting and come back in and try one more time. And otherwise, I'm almost done. So then I might just finish without slides. But I'll be right back. So I am back in the meeting. I am sharing my screen and
that's good. Yeah.
Good. I was worried there for a moment. Okay, so everyone sees my slides now with the 3 green boxes.
Yes.
Thank you for letting me know, Jonathan, and for everyone for helping. Yes, so naming what component are we calling active inference, and also beliefs and priors, where do I put them? And where should users put them? Because I want to make it natural for people. Good. Notably, as I said, you can use the same generative model with different perception processes. And so, of course, the standard is, and so on. So it should be, at least I believe it is modular enough that we can program it as modular, so that you can switch one out. You could say, for my perception, I want to use sampling instead of variational base. And in principle, the rest should work just as fine, although it would take ages if you want to do sampling and having to run it every time step in the future. Of course, the standard is that we're using handcrafted components. So we've coded our own generative model, we've coded our own, or that is, we've copied the perceptual inference process, the variational inference process from pymdp, which in turn comes from the original MATLAB code, but it's still hand-coded our own variational inference, and also hand-coded our own optimization scheme, this coordinate ascent variational inference. And we've hand-coded the tree search through policy space also. There are many advantages to using handcrafted components. So one is that we know what they do. Another is that if necessary, we can make them specifically compatible with other things. But there is software out there specifically for doing variational inference and specifically for optimization schemes and tree searches and so on, that we should in principle also be able to use if we want, and which might speed things up, for example, or make us more flexible. I'll return to that. I'll return to it now. Just to give a sense of what's out there. So the SciML, so science and scientific machine learning ecosystem is very well developed in Julia, which this optimization.jl package collects all the optimizers in the whole Julia ecosystem, which is hundreds of them. That we might not need that many, but you could imagine that some of them are more faster or avoids local minima better than the handcrafted one we've used. Might also not be the case for this, at least for the specific POMDP model we're using, but also in general for other kinds of generative models, they might be the case. There's also tools for differential equations, etc., which we could use if we want a generative model which consists of differential equations, and I'll return to that. Then there are tools specifically for Bayesian inference. I'm most familiar with Turing, which makes it very quick and easy to write a generative model, which can include almost any kind of Julia code. So you might indeed put differential equations just in there, or other types. And then you can do either sampling or variational inference in Turing. I know Turing is optimized for sampling, but it has a somewhat extensive variational inference tool. And that means that in principle, you could use Turing's variational inference as your perception process. And that would immediately allow you to use any sort of generative model that can be implemented in Turing, which is very broad. There's, of course, also tools like RxInfer. So I've been asked quite a few times, what's the relation between ActiveInference.jl and RxInfer? And I got back to it, but basically RxInfer offers very efficient belief updating that you can use for the perception part. You can also use it for the prediction part, and maybe for the action selection part. I'll return to that. But basically, we could rely on this as a backend for doing the variational updates, belief updates, which should immediately allow us to implement a wide range of generative models if we so decide. There are also others. So Gen looks very promising, but that's a much more low level. So supposedly you can make things very, very efficient there, but you also have to do everything yourself. And there are also tools like Neural Estimators, which is a software library specifically for amortized inference. So where you have a generative model and you train a deep neural network to produce posteriors for you. I haven't used it, but I know it exists and I know others use it. And that could also be used as a perceptual inference process, where we just say, yeah, just plug in your neural estimators, a deep neural network, and it will pass out the new beliefs. A bit, I think this is what people are doing in deep active inference, although that's another place where I'm a bit unsure. Notably, since Julia is auto-differentiable, we can use that to do optimization and Bayesian inference over almost any code, but there are many optimization backends, a whole range of them. Maybe the most exciting is Enzyme, which we're relying on, which is fast and language agnostic. And of course, there's an ecosystem with plotting and data handling and so on. But I think the first two are the primary resources that are important to make aware. Okay, so now I'll just give a little sense of the types of models, types of perceptual processes, and types of active inference variations that I know of. and I should also finish soon. So after that, I'll round off with a sense of the implementation ideas we have. But this is kind of the core structure. So generative models, the classic one, of course, is the partially observable Markov decision process with discrete states, discrete actions, and discrete observations. There's also things like generalized filtering, not my expertise, but it can be used as a generative model and used exactly as any other generative model, except it will have, or it can have, continuous states, continuous observations, continuous actions. The hierarchical Gaussian filter is a type of perceptual inference process for a specific type of generative model. So these networks of Gaussian random walks, where instead of doing gradient descent, you can analytically calculate the minimum of the free energy with some approximation. And that's nice because it's faster, just jumps right place, and also happens to be precision-weighted prediction errors. And you can, in principle, combine this with partially observable Markov decision processes. We have some work on trying to kind of put the HGF into the larger family of active inference. Yeah, we'll see. That's for another meeting, I think. Predictive coding networks are, I suppose, also just a generative model consisting of many states where you have Bayesian posteriors and Gaussian posteriors and Gaussian, and so Gaussian states with Gaussian posteriors, etc. But they can also be non-Gaussian. I've seen papers now on Poisson, for example, nodes in predictive coding networks and so on. There are also theory of mind models, and in this context, I mean theory of mind in the explicit sense that you have a generative model which includes another person having a generative model and doing perceptual belief updating in your generative model. And I've done some work on this, where you need to find a way to be able to do Bayesian inference over someone who does Bayesian inference, but luckily, of course, tools for that exists in the applied cognitive science world already. So in principle, it should be possible. It gets complicated very quickly, many parameters to include, and especially if you have recursion, etc. But it is just a type of generative model. And finally, of course, you can use any generative model that can be implemented in something like Turing or RxInfer or Gen. And I just note that I at least think it would make sense to sort these generative models primarily based on whether their actions, observations, and states are discrete, continuous, or both. Because some action processes like the tree search will only work with discrete actions, for example. Perceptual inference, we can use analytic, as we do in the Dirichlet parameter updates. I think RxInfer uses that when it can. We can have our own hand-coded variational inference, often with gradient descent on the variational free energy. And when we do that, we also hand-code our own gradients and our own optimization scheme. But in principle, we could use Julia's autodiff for the gradients or SciML for the optimization scheme if we wanted to. There are also hand-coded analytic approximations, like in the HGF. And we can rely on external software like RxInfer, Julia, Turing, and Gen. And then, of course, we could, if we wanted to, use MCMC and amortization. If for some reason we decided that that was useful, of course, that departs a little bit from the kind of classic, fully principled active inference, which works on free energy minimization. And finally, you can have these factorized message passing based models. Again, this is not my primary expertise except in the context of the HGF, but notably where you can have, so you do updates for each state in your generative model. So you have a whole network of generative model of states as your generative model, and you can do updates for them in principle in different ways. So you could use analytic where it works, for example, for the Dirichlet parameter updates, variational inference where it doesn't, and maybe amortization where necessary, or something like that in principle. And again, some of these will work only with some types of generative models. So if we're going to use RxInfer, it has to be implemented in RxInfer. Of course, you could implement a POMDP in RxInfer and then use it here. Finally, for the action selection process, so the active inference, or the wondering what to call this still, we have quite a few things we can change. So one is whether to use vanilla sophisticated inference, and then there are a bunch of settings once you've chosen to do sophisticated inference. For example, that we needed to set a threshold for cutting observations and so on. We want our, I've called it planning method, which is the tree search, where you go through the whole tree and you and that of course only works with discrete actions observations, or I suppose if you had continuous actions observations, you could just sample from them and make a tree like that. I don't know if that's would be useful or not, but could be done in principle. But you can also do an optimization approach. So of course, what you actually have is you have for each time step a variable, or which is an action. Or of course, if your actions are multivariate, that's a multivariate variable. But you put into a function, and if that function runs your sophisticated inference ahead in time and just returns the expected free energy, you could use any optimization structure for that in principle, and that might be what one should do if one were to use continuous actions or continuous observations. You could also even, I suppose, in something like Turing, which is a sampler or a variational inference, you could simply use the expected free energy as the negative log likelihood, and then run a normal Bayesian inference process, and that should give you a full posterior. I think I haven't tried this, but that's something we want to do. Full posterior over the actions, where you treat you do inference where you treat the expected free energy that's a consequence of your actions as if it was the log likelihood when you calculate your posterior. So those are mutually exclusive, those three, but they should work fully orthogonal with the rest. There are also different types of optimization objectives. So the expected free energy is the classic, but of course this the generalized free energy, and I haven't had the pleasure to read through that paper in full. So I'm a bit unclear on whether it's primarily an optimization objective for actions, or whether it also matters for the perceptual inference component, and whether that requires other things to change. So that's a question that will come in a second. I also know there's something like David Hyland's path divergence objective, where he makes an alternative to the expected free energy that also assumes or penalizes the energy cost of updating priors to posteriors. You could, I suppose, also just use the expectation of the free energy, which, as I understand, has some downsides. And one might, in principle, have new optimization objectives in the future. And that, like I said, that's orthogonal or modular with the rest. There's inductive inference, which, as I understand it, is just penalizing states that are not likely to lead to some goal state that I have a prior over, on top of the other components of the expected free energy. We might also have some heuristics, I've called it. So this was when John was going through, because the tree and sophisticated inference can quickly become pretty large. And so you can save some time if you can immediately throw out some policies before kind of evaluating them. And one could either just ignore them completely, which is less principled, or, for example, add just set the expected free energy to infinite or something like that for, let's say, for example, policies that would leave the grid in a grid world. So impossible things. And finally, there should be setting here whether you want to keep all the intermediate values to keep the full explicit graph or not. And the claim is that this is all fully orthogonal to the choice of perceptual inference and the generative model. And that's why they should really be specified as separate components. Yes, and inductive inference and generalized free energy, I haven't read up well enough. So if I'm kind of getting it completely wrong here, if they belong somewhere else, that would be nice to know. Finally, there are some ways, and I was just looking at RxInfer, where you can do the action selection and the belief updating in kind of one inference run. It's what's called planning as inference, I believe. And so here's a section from a model from RxInfer, where notably you just specify the model. They have tools for doing Bayesian inference on it. And this is a classic POMDP, where they then add the goal prior here. And so you're going to infer actions and beliefs that will make your final state be as similar as possible to the goal prior. And that's very nice and useful, and etc. I'm under the impression that this doesn't involve an explicit information gain component, although it might be wrong. And I'm pretty confident that it does not involve sophisticated inference, because in sophisticated inference, you have to run your inference process, perceptual inference process, as part of your active inference process. And that, at least I think, can't be done, or at least is not done here in the RxInfer tool. So this can be accommodated. We can just have an action component that just takes the posterior that is resulted from this model and samples from that an action. But I think the primary question here is how basically the relationship between planning as inference in this way and other types of active inference. Because of course, if this is where we want to end or something like this, then the split here might make less sense. Okay, I'm essentially done. I'll just say that we have another package, action models, which will take care of all the cognitive modeling and also provide an interface for agent-based simulation and gym environments that can be used with active inference and any other model type that takes observations, produces actions. And I've been working with that. It's a sister package that's compatible with ActiveInference.jl. There's people involved in this, which I'll just mention here. And that the hope is basically that a user will create an active inference agent. So this is just dummy code. By kind of choosing the generative model, the perception function, the prediction function, and the action function, and combining them in this way. And in this case, I'm pretending that we have a module POMDP, which then supplies functions that can be used for this. So if the user doesn't want to make up their own, there's a library of already created functions. And we have those for the POMDP, of course. And notably, I'm not putting POMDP in front of the action because sophisticated inference and active inference is not specific to the POMDP generative model. Notably, you could even, if you were a bit naughty, put in non-active inference components here. So expected utility as your optimization objective or something like that. Well, I'm not sure anyone will want that, but it should be an option at least. And then we aim to kind of then produce, sorry for the misspelling this, but produce a high-level constructor similar to the standard call in pymdp, where you just write, I want a POMDP. And then I put in, so you have a constructor that takes the details for all the components and then just puts them in the right places so that users can, if they want, just use a classic POMDP. So this interface will be very similar to the one that exists now, but just as a different, has this structure in the back. Notably, we could put calls here where you say, as backend, I choose between hand-coded, which we've made, or Turing, or RxInfer, and then behind the scenes, the POMDP will use those tools instead of a hand-coded model to create the POMDP and do the inference. Okay, sorry for going a bit over time. I hope you can forgive me for that. And we're done now. Just reminding us that the primary question is whether this structure here makes sense and whether we're getting at least most of the field with this application overview of the 3 types. Also whether I've got something wrong in general, something we've missed, and especially if there's some features in the literature that I haven't heard of that should obviously be in a package like this. And if there are thoughts on how to make this easy to contribute to for the community. And then I have some references, not a lot, but just for the things I thought people might not be familiar with. And apart from that, thank you very much for the patience to endure all this blabbering. And I look forward to hear what you think. Thank you.
Excellent. So perhaps we can unmute and deliver a nice round of applause to Peter.
Thank you, Carl. Saving me the social awkwardness of having to say that myself. It's appreciated. Okay, so normally now we have some time for feedback and comments from the audience, and then Carl usually summarizes. Do you want to keep that structure, Carl?
Yeah, it might be best if you don't share the screen, you can manage your own question and answer, and then when it comes around to me, we can whip through the slides again just to pick out the particular questions. Yeah. Okay.
Thank you, Carl. All right, Mark, you have a hand raised.
Yes, thank you very much. Great job. I'm very interested in the model that you put up, where it has the generative model and then perception, prediction, and action. and this is just, I'm trying to get a better understanding of all of this, but I appreciated, first of all, that it sounded like you were kind of wondering, okay, what's part of the general model? Are the priors then part of the generative model? I think that was a question you'd had. And I wonder the same thing. I kind of just picture the generative model as just sort of absorbing all of these outputs and inputs and just kind of growing and becoming more and more efficient, I guess. But I also wonder and this is reflects my understanding. I thought perception was actually the prediction. I thought those were almost the same. So I'm having trouble conceptually seeing those as separate, and just kind of wanted to try to refine my understanding there. If you could speak to that.
That's a very good question, and it immediately tells me that what we call these things is really important, and where we split them conceptually. So that's helpful actually already.
Or do we split them? Right, is my question, particularly for perception and prediction. I thought that prediction this is what I think I'm seeing, for example.
And I will see maybe what Carl says in a moment on this also. But the reason I chose to split them up is just because in the code we have two different things we need to do. One is to make a guess about what the world is like based on some observations. And I've called that perception, but maybe we should call it belief update or something like that. And then I have another function that calculates what is likely to happen in the near future, given the state that the world is in now, according to my beliefs, which is the one I call prediction. And at least, so when theorizing about what our experience is, as far as I know, it's usually that it's the belief about what the world is currently like. That's also what we experience. And so the prediction about the future is perhaps not. But so it's a whole different question, basically, which part of this formal framework is directly related to conscious experience. And I think there I don't have a strong, I know people are kind of arguing. Yeah, but so it's a good point. Maybe one could join the two under perception and call them belief update and prediction, for example. That might be a way to go about it. Yeah. And I'm sorry this was so technical, Mark. I hope at least a little bit of it was useful to you.
Oh, I survived. I'm better for it. Thank you.
Because it's feedback on the software, and so it necessarily becomes a little technical. But yeah. Thanks for the question. That was useful. Okay, Andreas.
Yeah, I'm very grateful for Mark's comment. I thank you, Peter, for your talk, and thank you for your team. I've read the Active Inference textbook, but I probably won't be coding anything until maybe when your software comes out, or so, like, I don't know, maybe in a year. So that's I'm maybe, and your audience. I found many things clear in your talk, but I think what Mark said rings very well with me. Like, that would be clearer if there were those three divisions, and then you could have a subdivision, maybe like you were saying, like between, because that's not for me, that's not a conceptual division. That's a technical, like that's almost like a problem of coding, like, so maybe to separate out, like, these are the conceptual divisions in the model. And then, of course, when you code, like when you have to worry about technically coding, that shouldn't be something you're worrying about when you're looking at things conceptually, because it's very distorting if you because you start to think that, oh, these are separate things, whereas maybe the whole point of active inference is there's the same thing, right? So to separate out like things that have to be done technically separate because for practical reasons, but to make that very different than the things that are conceptually, theoretically considered distinctions. So that's what. And then maybe as a user request to say, and you mentioned maybe theoretical thinking, but like in modeling this, to be able to just have a way of writing down comments, maybe in the very beginning, saying, okay, I'm going through the whole model and these are my little notes. And then I'll see them all mapped out. Like, okay, these ideas are in the, this breakdown, and these are in this. And so if there was just a very simple way to write down text comments, and then to be able to, just for your own sake, say, okay, I'm trying to learn this, and this is where I'm putting things, and now will it make sense as I shift over to either writing code or plugging in code or whatever. I would find that as a newbie useful, I think.
Okay. And are you imagining that the software itself provides a way for writing comments, or?
Well, I mean, obviously it provides a way of writing comments, I suppose, but to do it in a way where like you're kind of invited to, it's an invitation to, like, here's a particular, if you write these comments this way, you get some, like maybe it makes a diagram out of them, right? Or it makes it, so it fills in the picture, like it's colored by numbers or something.
Yeah.
So, it would be, I would find that very, like to say, I'm not lost in my creative thinking. I'm
Yes.
thinking creative, and then I can show it to somebody and say, okay, how do I start coding, right? So it'd be communicative.
Yeah, so maybe even I'm thinking aloud now, but it sounds to me like you're suggesting some kind of a learnability tool in it, right? So you can, like, meaning that it can show you where you are in the process or how things fit together, and maybe even
Well, it's just, if you don't do it, I will have to do it by myself on my own paper or computer screen, right? And so, okay, and if you're an expert, you just do it in your mind, right? But if you said, look, this is natural, that you would want to write it out, and then you can show somebody, or maybe AI can give suggestions, or whatever it is, right? But that you have a way to.
You could imagine even having something like a drag and drop or something where you like, for the action selection part, I want, sophisticated inference. You click that and you can see some information or something like that. I mean, I'm imagining, I don't know if that's a good idea, but
It could be like a questionnaire, like 10 questions or something.
Yeah, exactly.
How are you? Fill it out, and then so it doesn't have to be.
Yeah, exactly.
I'm thinking
like
simply.
the software asks you questions, you answer them, and then you have the model.
Well, you just see the list of questions. Here's 10 questions. I can keep them blank, or I can keep them, but if I fill them in, I'll have filled in the whole picture. I'll fill in the picture parts I want.
That's a good idea. That's a good idea. And thanks for the other comment also. I think basically, I think while this is a technical tool and meant to implement something technical, it's also conceptual, because it's the interface that a user of active inference modeling will meet. And so we have to keep that correct and intuitive and in accordance with the theory, right?
And that's
good.
Your concern about the names, right? Like you could give any old name to anything, but it'd be very disruptive, right? Exactly. Like it'd be very hurtful. So you're really trying to do that.
Yeah. Thank you, Andreas. All right. Are there other questions or comments from the audience? And luckily I have Sam and Jonathan with me here, so in case I do something silly, they might catch me. Yes, Andreas.
Back in mind. This is, I think, like, the goal is to do the vanilla version. But I just wanted to say, you got me thinking, and I don't know if this fits within active inference or not, but this would be pushing your maybe. But I think a lot in terms of a learning cycle. Okay, like I take a stand, I follow through, I reflect, like a scientific method. I have an hypothesis, I do the experiment, I look at the results. Now, that's not quite an action perception loop, because it has this step of taking a stand. Okay, so the action perception loops, absolutely important, and etc. But there's something more conscious here. And so the question is, like, what difference is that? And so one way to do it, and one way to incorporate that kind of possibility would be to say, well, this is just a fancy action. So this would be like, version 2 when you do it, like to be sophisticated action. But what it's basically pointing to, it's saying that when we have these belief models, a lot of times, maybe like the belief model and the facts we're seeing are not quite related. Like, I have a belief about what a person is thinking, but I only hear what they tell me. I never get to hear what I think they're thinking, right? I have to separate those two. So I have an objective, like, this is what I heard, and then I need to switch modes. Okay, but what do I believe? And do I adjust my belief? So like this parameter, I think like in active inference, it might say, the whole game being like, well, am I going to update the world, or am I going to update my belief? Well, but maybe I have a parameter, you see, that decides, like, see, if I have a hypothesis, it's saying, well, I'm not ignoring reality, but I'm adjusting a little bit, so I'll, or like, you're not supposed to erase data points, right? Some scientists do that, but so this idea that I have my own stand, right? And then I choose my options, like I design my experiment, I choose the experiment I want to do based not on what I heard, but what my new stand is or my old stand is,
Yeah.
have I to change my stand yet, or I'm sticking to my guns, you see. So I don't know how radical of a difference that is to active inference, if it can fit into that kind of software, but it's just adding that layer of cognizance in there.
Yeah. So thanks for the comment. So I think at least my impression, without knowing the framework and the terminology you used with taking a stand and so on, my impression is that it would fit very well.
Okay.
In the sense that in active inference, there's always this balance between how certain you are of your prior beliefs and how certain you are that you should trust the observations you get and how you balance them. And that at least sounded similar, right? That sometimes he will say, yeah, I'll help you with that. But you know him well enough beforehand that you will know that it's probably not going to happen, or he might not mean it, or something like that. As an example, right? Yeah.
So in terms of the code, I think what it's saying is that, like, if you're really trying, like, you make these very careful conceptual distinctions. You separate that out from technical issues of programming. How because you're incorporating different softwares, etc., that aren't using your conceptual distinctions, but you want to be able to use them. But then to say, like, okay, so what are the classification or categorical points that come up, like where, like, is everything in the environment, like, is there a distinction between facts and beliefs? Let's say, is there, like, do you have to worry about that type of distinction, or when do you do, like, or when does it become an issue, etc.? Like, your software can just simply either just say, look, this is what we do, or it could say, look, here's where it gets more complicated, and here's where you'll have to be more finessed, and here will, like, so you try to keep it simple as possible, and you don't have to support more complicated things. But if you do, you kind of start to organize it to say, look, here's a categorical difference you're going to need to make if you want to do that. Now you're going to. So that's a thought.
Yeah, that makes sense.
Thank you.
Yeah, so basically, if and where the structure starts to break down, that has to be very explicit.
Yeah.
Package in the documentation and so on. Yeah. Okay. Thank you, Andreas. It's appreciated. All right. If there are no other questions or comments, then I think it's your turn, Carl.
Good. Is it my turn now?
Indeed it is.
Okay.
As usual.
Yeah, excellent presentation. And as usual, a lot of things to cover. So I'll just make some general comments, stream of consciousness, and I think we should go back through the PowerPoint, picking up on the green boxed questions. So general comments, I think this is an important initiative, and just strategically and sort of meta-scientifically, you're situating this development in the context of TAPAS and the TNU, I think, is in a very important move. So from my perspective, as a seeing how this technology can make a difference, I think you could summarize your ambition. It needs to be socialized. You use the word democratized in a slightly different sense, in the sense of developing the code. But I think the big step is the socialization of the application of active inference in a way that actually makes a difference and helps people. And the obvious, if you like, proof of principle or starting point would be computational phenotyping. And that has been most developed in psychiatry, where there's a clear clinical motivation to phenotype somebody in terms of their prior beliefs. But one can also imagine other applications beyond psychiatry and then beyond medicine, just being able to formally completely characterize somebody in a way that allows you to predict their choice behavior, has obvious applications in a commercial sphere. So there could be potentially lots of money to be made by somebody, but before you get to that, you have to socialize it at least in one community, and I think computational psychiatry is the right is the right way to do that. And also, maintains your amateur standing in terms of professional integrity and good citizenship. I think that's important. Implicit in that is a focus on what you want to do. Now, and I say that because a lot of the things you brought to the table are just other words for the same thing. And a lot of the options and developments, extensions, generalizations, reaching out to other packages or other theologies is unnecessary. You already have, you already have the machinery to address many of these things. So, just before I forget, you don't need a separate reinforcement learning, Julia. You can do reinforcement learning in active inference. You just switch off all uncertainty. It is provably true that in the absence of any ambiguity and epistemic uncertainty, the active inference just is an instance of the Bellman optimality principle. So you don't need to have a separate toolbox. You just need the ability to switch off various uncertainties, and you've got a reinforcement learning toolbox. And that may be an important part of the socialization. So saying that this is a package where you can either do reinforcement learning characterizations of responses to a game reinforcement learning paradigm or an economic game theoretic paradigm, or if you want to, you can start to switch on the added functionality or the generalization afforded by active inference and start to introduce ambiguity that converts your MDP into a partially observed MDP. Or if you really want to go the full hog and actually do active inference per se, then you can you can sort of include the implicit information gain or epistemic parts of it. And just on that, before I forget where I was going, all the special cases ranging from RL through to full active inference are basically achievable in a formal and unambiguous way just by setting various terms in the expected free energy to 0. Right. So if you there are 3 basic terms in this expected free energy. If you just take the expected value or expected utility or negative expected cost, which is just your expectation over the your preferred outcomes, then that just is expected utility. And that is exactly what is optimizing Bayesian decision theory. And it is, if you like, the equivalent of reinforcement learning. Remember, reinforcement learning has acquired its own meaning in machine learning, but reinforcement learning is behavioral psychology that should comply with optimal Bayesian decision theory. So all you need to do is to convert your reward function into a log prior preference. Job done. You don't need a separate package for that. Were it not for the fact that some people like to work with continuous state spaces, so your job there is just basically allow people to convert their continuous state space formulation into a discrete state space formulation. So that will be one socializing move you really have to focus on, is to showing how people can take an Q learning or an RL risk or a Wagner like setup and say, now let's just discretize this. So we can sort of bin the reward, continuous reward, into 8, and just show how to reproduce Q learning, for example, or risk or a Wagner in a discrete state space. And then you can now talk to people in optimal Bayesian decision theory, and you can talk to people and also talk to people in behavioral economics in terms of expected utility theory. Now, if I switch on another one kind of uncertainty, which would be the uncertainty about the consequences of my action. So if I'm not sure what's going to happen next, if I did that, then we have something called risk-sensitive control or KL control or path interval control. So this is sort of grown-up optimal Bayesian decision theory, which goes beyond reinforcement learning. But it would be the kind of optimal control that people in control theory would understand and would be used generically, say, in robotics or any control theoretic. So now we've got the KL divergence between what you want to happen and what you think is going to happen if you did that. So this is a step up from, by just switching on or adding to your expected utility or subtracting an expected predicted posterior or log predicted posterior over the outcomes. And now you can talk to people like Bert Kaplan and I'd say control theoreticians. And then finally, if you include the ambiguity, you get to the full 3 bits of the free energy, which can be decomposed into the information gain plus the expected information gain plus the expected cost. What I'm trying to say is that the whole point of the free energy principle and active inference is not to provide an alternative, but to provide a universal account of the way things behave, the way and what motivates them. And if you can find some other account that explains behavior, either that account is wrong or active inference is wrong. So we haven't found anything. What?
Or they fit, right? Or you can re-explain it as active inference.
That's what I meant. Yeah, if you can't reproduce exactly, and I mean, to working precision, any other scheme within active inference, then that's a problem. So what you want to be able to socialize is the idea you can do all of these things just by clicking switches on various contributions to motivated behavior, and thereby that would be, I think, one way of overcoming something you alluded to, and I'm not sure what you were alluding to, but I can guess it's the hyperexcitability and hypercriticality that you get in people who are committed to reinforcement learning, I presume. So you can diffuse that just by saying, no, this is reinforcement learning. It's just you have to switch off this and this because you're not interested in that kind of uncertainty. And that's, and in many instances, and particularly sort of, when you have unambiguous cues, you don't need the full, you don't need the full reinforcement active inference scheme. And you will get identical results whether you're using RL or active inference, simply because there is no uncertainty about there's no ambiguity about your observations. And furthermore, in many game theoretic situations, you can possibly eliminate any uncertainty introduced by committing to a particular policy. So very often the reinforcement learning solution will be exactly the same as the active inference solution. So if people can see that happen, then I think that will be a unifying, cohesive, depolarizing move that is going to be an essential part of the socializing. And again, before I forget, seeing it happen, I think is one of the most potent ways you can do this socializing. So once you've got your favorite examples under the belt in the ActiveInference.jl, I think you need to have tutorials, video tutorials, where you're actually filming yourself stepping through, clicking the buttons and getting the results for 3 paradigms you think are going to be predominant in the communities that you want to talk to. A couple of game theoretical ones, a reinforcement learning one, and possibly and that brings me to the point, who are you doing this for? And just to come to Andres's exchange with Andreas, I think you're doing this for people who want to have their questions answered, and that means you are committed to a particular application of active inference, which you sort of surfaced, about a third of the way through the presentation, which is this notion of meta-Bayesian inference or meta modeling. So we're not just building little synthetic agents that are, make really, really good decisions, and indeed learn how to make really, really good decisions. That's not the point. The point is you're using this description of Bayes optimality in its broadest sense, encompassing both optimal experimental design and Bayesian decision theory, as a generative model of somebody's behavior. So I think it's important to just keep reminding yourself of that. Otherwise, you'll get very distracted. You could make software that does optimal control and sell it to the oil industry for plant control, and we do it really, really efficiently. That's not I don't think that's the kind of socialization you mean. You mean this is for scientists who are possibly not even scientists, but people who want to phenotype, to characterize somebody on the basis of their observed behavior. Now, that simple objective means you are now in the world of meta modeling or meta Bayesian inference, and this is where your response and your perceptual model come in. I actually prefer objective and subjective models because of the confusion about the use of the word perception and perceptual. So AI gives you the generative model of a decision. So this is the subject. This is the experimental subject, the person you're trying to sell this product to, or this particular addict, or this cohort of people with obsessional compulsive disorder. These are the subjects of inquiry. They have their generative model upon which they make their decisions, or under which they make their decisions. And then you have you looking at this subject as an object. So now you have your objective generative model, which is basically the way in which their behaviors is measured. So it could be an EEG setup. It could be some way in which you've recorded their reaction times. It could be some way in which you've summarized their choice behavior in terms of the frequency with which you choose that, given that kind of trial. So the objective model is usually much simpler than the subjective model, which is the generative model of the subject. But you also have to specify your experimental measurements of that subject. And as soon as you do that, you're implicitly invoking another generative model, which now maps from the responses of the subject, which are latent because they could be EEG and neuronal responses that then map to some measurement that you, as the observer of that observer, hence observing the observer, hence the meta-Bayesian problem, bring to the table. That's quite a special problem, and I think it's and that basically I would leverage that specialness to make ActiveInference.jl stand apart from the rest of the field. You're not going to write software that sort of outperforms auto diff or sampling or whatever, or does Bayesian inference or replaces KL control in engineering. There are generations and millions of people doing that around the world, but there's no one developing software to do this meta-Bayesian inference, to do the computational phenotyping, and that I think should be your secret sauce, or the thing that distinguishes you from somebody else. And in so doing, that forces you to ask, well, what kind of, well, before I say that, there's a principal motivation for why that would be ultimately the most, well, certainly it's by definition a high order application of inference, in the sense that you're now making inferences about inference machines. You're observing the observer. And in making those inferences, you're using Bayes optimality all the way down, not just in terms of explaining this person's behavior under ideal Bayesian assumptions, but also using optimal Bayesian tools to infer what that of the subjective model was. Why is that a universal approach? And then you appeal to the complete class theorem, right? So what the complete class theorem says is that for any observed set of responses or behaviors and any set of loss functions of a subjective kind by the subject actually making those decisions, there exists some prior beliefs that render that subject's responses Bayes optimal. What that means is the only unknown, if you want to completely characterize this thing, is the priors that constitute its generative model, prior preferences. There is nothing else. Which means that if you can solve the problem of estimating what prior beliefs did this artifact, person, community, what prior beliefs or prior preferences best explains this behavior of this thing, job done. There is nothing else you can possibly bring to the table. There is no law that exists. So if you can solve that problem, you've basically solved all problems that can be solved via the complete class theorem. So this is quite a subtle, but I think important argument. And it's not just building a Bayes optimal simulator. I repeat, this is not about optimal control or robotics. This is about being able to characterize anything in terms of completely sufficient characterization in terms of the generative model and specifically the prior preferences implicit in that generative model that provides a complete and sufficient account of this thing's behavior. And notice under the free energy principle, you'll never know what's under the hood because it's got a Markov blanket. So all you have access to is the observable behavior. So if you can solve that problem, as I say, you've now solved all problems that are solvable. And then showcase that in the context of, say, computational phenotyping in psychiatry as the first step. So with that in mind, I'll just make another point. If that is the agenda, what kinds of observations of the things that you want to make inferences about in this spirit of meta-Bayesian inference, what kind of behaviors are you looking at? Are you looking at the way they throw a ball? Are you looking at reaction times? Are you looking at their choices? What kind of observations are you trying to, will you have to inform your inferences about this person or this thing's prior preferences? Can you just answer that? Give me your first three obvious and most important. What do people actually do? So your friends in cognitive science or computational psychiatry, what do they actually measure?
So classically experimental decisions. And that's usually discrete and so on, right?
Okay. Right. So you've answered the question. You don't need to go on. So you don't need to worry about continuous models.
But it's moving in that direction, and it's a movement I would like to help with as well.
What's moving?
I think the field, at least in some of the circles I move in, let's say, people want to also be able to model continuous behaviors.
Like what?
Like dancing movements, for example, or I would say, I haven't heard of anyone modeling, but so I think it's a kind of an unexplored frontier that at worst is ignored and at best is wanted to work with. But I think exactly because there are no models for continuous behavior, no one models it.
Right. Well, I mean, can I just push back? That's not true. Active inference was first introduced with continuous movements, handwriting, singing, and it generalized and leveraged a well-understood literature in controllers inference and AL control. There's and that's where all your generalized filtering or filtering in generalized coordinates of motion. That's where the original active inference MATLAB code came from, SPM_ADEM being an example. Now that's covered in more depth than discrete state space Markov decision processes. Ask yourself why it was never pursued. Why has it never been used?
That's been a question in my mind for a while, but I don't have an answer. Is it because it doesn't work as well? Or
What question could you ask? Let's just take the dancing.
Yeah.
What question? Okay, I've got this person here, and I'm now going to create a generative model of the way that they draw a house.
Mm.
What question you're asking of that person?
I suppose you can look at not with the house, but expectations of volatility or uncertainty in the environment. I think is something people are interested in on a continuous observation scale.
Okay, let's imagine something close to dancing. Let's imagine I've got a paradigm in which I have to point to a target, but under some perturbing force.
Yes. Yeah.
What question are you answering?
And if this is a trick, or not a trick question, but a question with a pre-made answer, then I feel embarrassed to miss it.
Well, I mean, those paradigms I have been used extensively for decades, and sort of people like Daniel Wolpert. So these are sort of motor control paradigms where you have motor schema and you have forward inverse models, and you want to know what kind of Bayes optimality underwrites these kinds of pointing movements or dancing movements. So, but I repeat, if the name of the game is to provide a tech that allows people to test their scientific hypotheses, what hypothesis could you test using a continuous state space generative model that was able to reproduce reaching movements, for example, or dancing movements?
How about something like how people learn about, for example, dancing partners, and if they expect them to be reliable sources of, like, basically if they expect them to be noisy or not. So there's an uncertainty or volatility learning, precision learning in other people's movements also in these cases, right, where you have to predict what other people do in this low level thing. But is it that you think it's too sensory motor and too far from decision-making processes and so on?
I think it's too far. I mean, you're right. This is a fascinating area, and you can get into Edda's world of synchronization and the estimates of precision and all that. I'm just, in terms of focusing on what you're going to bring to the table, is this typical of what people will actually want to know of their person who has addiction or autism?
Yeah. So I mean, I know there are people asking questions related to continuous things, also like pitch in speech in schizophrenia, or we have some continuous state action space models of social learning with some little object you have to plug on a circle and you get a cue and that kind of stuff. But I think you're right that the majority of experimental psychology, experimental neuroscience, computational psychiatry experiments are in discrete state observation space, and probably because they're simpler to work with, I would say. Naively thinking, at least from an experimental perspective, it's easier to have 3 buttons than measuring exactly where they put a.
Yeah, I mean, I don't want to drag this out into a, sort of, which could be a really interesting conversation, but in terms of answering the questions you brought to the table, I think that's right. I think that I'd even go further than that. That our generative models at the level where prior beliefs actually underwrite the kind of decisions that we make in our lived world operates in discrete state space. You're absolutely right. The way that we behave and move and talk and listen is in a continuous state space, but the interesting stuff is in a discrete state space. I can't decide 6.2 centimeters, but I can decide to go to the left.
Yeah.
So I get what I'm asking you to do is really just focus on what you want to deliver, because that focus will eliminate a lot of distractions. which you can revisit later in your life. But if you do get distracted, you'll lose focus and you won't achieve what you want to achieve in the short term. Because there's so much to do, even under the simple ambition of equipping the community in its extended sense with a discrete state space meta Bayesian tool, a phenotyping tool, a digital twinning tool. That can actually answer questions of the kind, does this person prefer this or prefer that, or does this person believe this or believe that? Does this person have this depth of hierarchical model, or is this level of abstraction completely missing? Categorical, is this person alexithymic in the sense that everything is either good or bad, or do they have 3 categories of people or 8 categories of people? Or are there 6 dimensions nearly all the questions you could ask are really all about sort of is it this kind of thing or that kind of thing? They're not continuous questions. They're not sort of well, you could argue that autistic spectrum disorder can be continuous, but that's the kind of way that you do your phenotyping, I think, is always going to lend itself. And what I'm trying to do is just to winnow down on what you need to accommodate and consolidate, and give you an excuse not to have to worry about that at this stage. And I'll just say up front now, why on earth do you need automatic differentiation?
Not if we're using a discrete state space POMDP model, I think. No. It was because I was considering, because it allows doing variational inference over a generative model, that's anything you can write in Julia would be the answer.
Right. But if you now are focusing on the kind of tech that people will actually use, and those people are basically doing trying to explain choice behavior, basically, then you will be working with discrete space state space POMDPs. I mean, in the title, it's decision. You're absolutely right. POMDPs can be continuous state space, but the kind of the decision that is made is almost universally a discrete kind of decision under a discrete set of options, and certainly in sort of in most choice behaviors, that's I mean, just think about the universal sort of paradigms, multi-armed bandits. If you could get have a generic MDP that almost built itself with a particular specification of your multi-armed bandit problem, there is no game theoretic or reinforcement learning paradigm that you could not model after discretizing it, because that is the most universal kind of problem. And it's got all the epistemics in it. It's got all the expression and exploitation dilemma, and yet it's a really simple MDP. You need to make it partially observable by having noisy multi-armed bandit problems. So if you can do that, that means that all your canonical demos and 99, well, say 90%, 80% of potential use cases are sorted, in the sense that you can use fixed point iterations and explicit updates, both for the belief updating and the learning. And I should also say, again, in response to the question and answer, model selection as well. That's an interesting one. So there are people, say Victorita, for example, who's done computational phenotyping with and without Bayesian model reduction. So you can actually take this sort of approach right through, beyond just inference and belief updating and decision making, to learning, right through to model selection using Bayesian model reduction. At no point do you need auto differentiation, and at no point do you need sampling. And indeed, if you try to use sampling to reproduce what are the most efficient fixed point updates you could possibly have mathematically, people would laugh at you. Why on earth do you want to use sampling when you've got the whole point. Give you another perspective on this. Why do people like quantum mechanics and quantum computing? The reason is it's all in discrete state space. That's what the quantization means in quantum computing. Why is it useful to be in a discrete state space? It means all your operators are basically sum product operators, and they're all linear.
Yeah.
Which means you never have to worry about nonlinearities. And furthermore, you can describe anything in quantum information theory. So if you can do it in a discrete state space, ignoring the dimensionality and the computational, the numerical issues, you've solved it in continuous state space. So that's why people are committed to, to sticking with quantum information theory and quantum, because the quantization just makes all the updating and all the maths really, really simple.
Yeah.
You never need. Sorry?
Lance had this good point that any dynamics can be described as in a transition probability matrix if you're in discrete state space.
Absolutely. Yeah. You can do anything. So you don't need to worry about differentiation. You don't need to worry about you don't need to worry about metric spaces. I'll just say, for your interest, the computational saving, the dimension reductions you can get by imposing metric constraints on those universal probability transition operators are the only reason why you might want to move to continuous state space, just to actually get the numerics down to sufficiently constrained so they can actually implement these things. So, this kind of discrete or quantum computing is not the answer to everything, because you can't actually realize it because they get too big. But mathematically, you can do everything in discrete state space. So as long as you keep your problems small enough, and that's the whole point about an experimental design, you're just constraining the space of choices to make it small enough to be easily computable. What I'm trying to argue you towards is not to worry about sampling, not to worry about auto diff, but to worry about what really matters, which is the different kinds of belief updating implicit in active inference, and in particular the meta-Bayesian problem. That to my mind is more important than making it, socializing it in terms of being inclusive. I can plug in RxInfer, I can plug in JAX or whatever. Yes, you can, but you don't need to if you just stick to what you actually want to solve, because you've got the most efficient way of solving it, which is just the vanilla active inference. Just to come to this question about carving things up, and is it sort of generative models, prediction, planning, and action? I like that because it really does sort of start to sort of factor things, in a way that people can get their head around and see different compositions. If I were you, I just stand back a little bit, though, back from that particular attempt to modularize the different schemes when trying to socialize, in terms of the headers on your YouTube tutorial. I just start with the first major distinction between specifying a generative model and then inverting it. And then the next step is using the inversion of generative models as an observation model in the context of meta-Bayesian modeling. So you've got your particular application domain is going beyond just solving or inverting a generative model. It's now doing that under different priors until you find the priors that render the actual empirical responses of your subject or population the most likely. So you've got sort of three levels now. Specify the subjective generative model, specify the objective generative model, inversion schemes for both of them, and then putting them both together in the context of meta modeling. So I think the sort of distinction between specification and inversion, or fitting, if you like, will be the first thing. And then now the functional form of your generative model now speaks to the different things that you're trying to carve up in terms of the generative model, the perception and the action and the planning, simply because, again, just standing back from the problem, if all starts with the generative model, and in this instance, it all starts with, it's grounded on the subject's generative model, or possibly models, if you're going to prune the models to best explain the behavior ultimately. And that tells you everything you need to know. Once you know the generative model, you then know how to invert it, because for every generative model, there's a graphical model. For every graphical model, there's a factor graph. For every factor graph, there's a variational meshes pattern scheme and a fixed point iteration scheme that will invert that model under certain assumptions about conjugacy and the mean field effect approximation. So the inversion of it almost writes itself once you specify the generative model. Now, so I would predicate the processes entailed by belief updating or inversion in terms of a decomposition on the nature of the generative model. And if you do that, then you just ask yourself, well, what is the overall factorization that currently attends all generative models? And you can either go to 3 factors, or you can go to 4 factors, depending upon how nuanced you want to be, whether you're talking to cognitive scientists who like attention, for example. So what don't you know? When you have to specify and write down your generative model, what do you have to specify? And what don't you know? Well, you don't know the states. You don't know, let's do the full, no, we'll just do the simple, we'll do the 4-way as opposed to the 5-way one. So when you write down a full generative model, that's a joint distribution over the observables, the real variables, and all the latent causes of those variables. They can include the latent states, the latent parameters, and the model itself. Under the latent states, with active inference agents, you've got this crucial distinction between states of the world and the controllable policies that the agent is pursuing. So now we've got a factorization of variables that we are now going to invert, that factorizes into an approximate posterior over states of the world, the latent states that are generating my observations in the moment. We've got a posterior, and this is crucial, a posterior of the policies or the actions that are entailed by those policies, but it's actually the policies in grown-up sequential policy optimization as opposed to state action policy optimization. You can make it into a state action policy scheme if you switch off the sequential policy optimization. But the key point I'm making here, that the unknown is the policy, and that's what makes it into an agent in planning as inference sense. You don't always have to have that. Well, let me go through. I'm half answering your green boxes prematurely. So you've got a Q over X, the latent states, or S. You've got a Q over your policies, and now you've got a Q over your parameters, A, B, C, D, whatever, right through to H. We'll go into that in a second. And you've got a Q over your model. So what does that mean? Well, it basically means that I've got 4 levels of inference. I've got fast perceptual inference, inferring the unknown states, updating my Q. I've got slightly slower future pointing, planning as inference, as I'm belief updating my Q over my policies or my actions, my control variables. I've got learning, as I update my Q over the parameters of my generative model, those things that don't change very much, very quickly. And then I got a Q over my model itself. And that's natural selection or hypothesis selection of the kind that you were discussing with Andreas. So, and you could put Bayesian model reduction, and you can make your model go to sleep. You can make it introspect, do a bit of pruning, and then relearning again. So now you've got a nice formal ontology of different kinds of belief updating that you can now put in your perception under the generative model, which would be the updating of latent states of the world. Planning is this updating the policies. There are other latent causes of your observations. It's just that you think you're in charge of them. You probably not, but you think you are. And then you've got learning, which are the parameters that change very slowly. And then you've got models, hypothesis selection, or model comparison or model reduction that the subject can do. They can invoke and do that sort of taking a stand and then taking another point of view without that particular perspective, and then see which is the best information. I think that would be if you like, a more useful way to frame your ontology, because it speaks directly to the various scheduled the inversion of the generative model, each occurring at slightly or at greater timescales. Specifically, the learning is always much slower than lots of accumulated experience before you can update your parameters, and the model is very, very slow because you have to accumulate lots of different parameters. Accumulate your parameters over a long period of time before you can find out which of them are redundant. Under that, so that would be one way of carving it up. And just to sort of connect the dots, in the absence of a posterior over your policies, but you have you've still got active inference in the sense that you predict certain, say, proprioceptive in a biological or IMF in a robotics context. It's certain sort of measures of your actuators, consequences of your actions. You can still do active inference, and that's the continuous state space active inference that does the drawing and the dancing and the pointing. And that's called control as inference. And then if you want to move to planning as inference, so there's no difference between active inference as you were describing it and planning of inference. That is planning as inference. Then that means you've got an extra factor in your generative model, which is a factor, which is a Q over your policies or your action. And I think that is definitive of an agent. So you can have active inference of a, sometimes people call it merely reflexive sort. So I just need to have reflexes there, and then I can do my dancing. I can just have my my Lorentz protractor on the inside, generating predictions of how I'm going to feel myself moving, and I can dance, and I can synchronize in exactly the way that we modeled Change of Bird Song, and we can measure that, and that's all very nice. But when we move to the next stage, we now actually have a posterior belief about my policies that contextualize that merely reflexive behavior. It's this set of reflexes or that set of reflexes. We move from this homeostatic to this allostatic kind of inference, active inference, acting as inference. So, this is probably not universally accepted, but in my world, there is a bright line between control as inference, and that's control theory, that's path integral control, that's from reinforcement learning, and planning as inference, which actually requires you to roll into the future. And that's usually under a set of discrete policies. Now, you can do this in continuous state space, and you can use a generalized free energy, but I don't think it's going to be very interesting, because you can get most interesting behaviors from this merely reflexive control as inference. When you move to planning as inference, then that is usually associated with discrete models, which is where I think you should situate yourself. You can do controllers inference with with discrete state space models. It's just usually very interesting because you want to get into the future, basically.
Yeah.
So that would, if you like, I think provide a nice endorsement of your sort of four-way well, distinction between sort of prediction and planning as being a reflection of the fact you've got this sort of factorization between states of affairs in the world and the policies that you bring to the table to navigate that world that are private to you. And the cause and consequence is the generative model and the action. So you now select your action from your posteriors over policies or paths, which is a sort of more general this kind of thing. If we now come back to what this looks like from the user's point of view, so okay, I understand. All right, so I've now got to specify the generative model, and once I specify the generative model, then all of these different kinds of processes may or may not be entailed, depending upon whether I specify that particular part of the generative model, and then you can explain to them, right, okay, so how do you specify a generative model? Then you have to specify the form of the model, basically the structure of the factor graph or the Bayesian dependency graph, and provide some priors over the parameters. And so now we're focusing on the specification because the inversion writes itself if you solve problems. So the specification. What is a specification? The way that it has evolved in active inference under discrete models in a way that can be easily socialized is the ABC of active inference. What do you mean by that? Well, what I mean is that any generative model has to be specified in terms of likelihood and priors. What are the likelihoods? Well, in a discrete state space, these are just specified by a mapping from latent hidden causes to observable outcomes. We call them an A tensor. Well, what are the priors then? Well, in this world, the only priors are that the world unfolds in a lawful way. And these are specified by probability transition matrices that we call the B tensor. So your job is to write down your A tensors and your B tensors. Why are you calling them tensors? Well, tensors are like matrices, but with lots of options or slots in. So what are the slots? Well, sometimes you could choose how the world transitions by acting. So the extra third dimension on your B tensors now introduces a belief over which particular slot or policy or path I'm currently implementing. How do I specify my prior beliefs of these paths? Oh, we have to introduce a C vector or a C tensor. Well, what do they mean? Well, these now define my prior preferences over the outcomes that would ensue if I committed to this path or this path or this slice of the B matrix. Job done? Well, not quite. You've got to still specify how you're going to initialize your inversion scheme. So we're going to have to put in a D now. Are we finished? Well, not quite. So once you've seen yourself behaving using planning as inference a sufficient number of times, you may actually habitize that, and you may now start to learn, I am the kind of thing that always chooses this policy in this situation. So you're going to have to specify an E, which will be your habit one. Have we finished? Not quite. Notice that we've specified our Cs, our preferences that define the goals in outcome space. Can we not do the same for the latent state spaces after we have learned the generative model? Yeah, absolutely. We'll call that F. Oh, we can't. That's free energy. Oh, we'll call it G, but no, we can't. That's expected free energy. All right, we'll call it H. And then we've got our A, B, C, 3, D, E, F, G, right the way through. And that now becomes a complete. So the H, incidentally, is that which is required for inductive inference, which was going to be, I think, an essential part of your tech. So you've now explained the A, B, C, D, E, F, G completely, and that's all that the subject now needs to be able to specify. Then you
What about whether to use sophisticated inference or not, for example? Would you say that's part of the generative model?
Well, yeah, it's certainly that is interesting. And I'm answering from sort of, circa 2025 implementation of active inference. So for the past few years, I have only used sophisticated inference. That's the only way to do it. So yeah, I mean, you can take it off, you can remove it, but you'll certainly you're usually only going to get sensible planning as inference and the sophisticated inference. So all the current code, which is SBM underscore MDP underscore VB underscore XXX, that's third generation active inference. It only does sophisticated inference, and furthermore, it just assumes that all allowable actions are always re-evaluated at every time step. So that means if you've got sort of 8 allowable actions or control variables, then you will, and you have a 2-step ahead, you will have a tree with 64, or 8 to the power of the depth of the tree. And of course, that could easily explode. The current implementations do all that clever heuristic pruning because it's not heuristic. You can actually use the free energy, the path of the expected free energy to prune unlikely paths. So all of those issues, have been addressed and solved and implemented in the third generation MATLAB code, which doesn't have, although it emulates, it doesn't have the original stuff that you've incorporated, which is the precision over policies as a dopamine thing. You can still get that, but it's if you like, it's an add-on. It's a sort of it derives what you would have got had you done the dopamine stuff. That dopamine stuff was really for people specifically interested in reward learning and dopamine. It's not a generic aspect of active inference. So all that went by the wayside, which is why we don't need any auto diff or differentiation or gradient descents. It's all simple fixed point iterations now. And it always does sophisticated inference, and the way that you turn things on and off is this basically by not specifying them. So if you don't specify C, it'll assume C is flat, so there are no preferences. It's all epistemic. If you don't specify H, it won't do inductive inference. But if you specify H, it will do inductive inference. So it just automatically detects everything. So you can sort of switch things on and off just at the point of specification. And of course, you can do that in terms of the precision of your prior preferences. And in a sort of generic situation, all these C's and H's and E's become tensors. So you can condition upon them upon states as well. So you get a lot more flexibility in the model specification. But what I'm trying to say is that if you teach people the ABC of specifying a generative model, they will have all the equipment and know-how that they would need in order to switch things on and off without having explicit switches. You can still do that. You can say, give me a full prior preference active inference planning as inference scheme, but switch off the ambiguity just to see what happens.
Or switch off sophistication, I suppose. That I suppose is that category.
You can. I'm just trying to think how you do that. That would just be one step ahead. No, I'm not. I'm sure you can. I'm not quite sure. See, the sophisticated scheme is just mathematically beautiful because it's self-calling. So the way it's coded, I'm not quite sure you can switch it off. Right. I can't quite remember how not to do it. Anyway, this is something that you can discuss with your colleagues and think about well, with John specifically in this instance. But it leads to a really simple fixed point iterative scheme that doesn't involve any gradient descent or anything. You can still do backwards induction with gradient descent should you want to, or at least actually it's probably not even gradient descent. It probably still is. No, there is a bit of gradient descent still there in the backwards schemes, but generally you don't need that. What I'm trying to say is that in my experience, if you've got long horizon problems, you would solve those with inductive inference, not with sophisticated inference. So I've never been in the situation of going beyond tree searches more than 2 or 3 deep. So again, in terms of guiding you towards what really matters and what's going to be useful, I wouldn't worry too much about all the heuristics that people claim to be exploring, doing very, very deep tree searches for active inference. They've all been already explored, and they're not actually heuristics. So there are lots of simple ways of limiting the tree search.
Does inductive inference and sophisticated inference exclude each other?
No. And exactly as you said, inductive inference just provides constraints on sophisticated inference. Perfect. So, inductive inference doesn't tell you what to do next. What it tells you is don't do that. So if I roll out into the future, and the key thing about inductive inference is that it provides constraints if you've learned a precise generative model. So it only kicks in when your belief structure about the transitions are sufficiently precise. So it will have no effect unless you know things very precisely, or you've learned them to be, and you've become precise. So that's you can only look deep into the future. And by deep, I'm talking, 512 iterations. Well, usually the default 64 iterations and steps into the future. But only if you've got sufficiently confident or precise knowledge about the transitions, which is obviously the only situation in which you'd want to go 8 or 64 steps into the future, because if you don't have precise beliefs about the transitions, you just lose confidence. Uncertainty just creates a level playing field. So there's no difference in the expected free energy at the end of the day, simply because you didn't have precise beliefs about what would happen if you did that. So inductive inference will kick in when you need to. But all it does, it says that if I want to be in this set of latent states specified by your H tensor or a function that plays a role of an H tensor, then under my very precise beliefs about forward transitions, I can actually work backwards by just transposing the B tensors and propagate things forward, backwards in time from my goal. So it's like a very kind of backwards induction. And then I can identify any state that's not in the set of states that can be reached from backwards in time from the goal. And those are the states that I have to avoid, because I know that there is no way of getting to my goal from those states. So that just gives you basically, that just sort of switches off a number of states to which I would transition to. And then within the remaining states, you do your sophisticated inference.
Yeah, that makes sense. Thank you.
So
Carl, Can you give me 10 seconds, because we have guests and I just need to tell them that I'm in a meeting.
Oh, I'm sorry.
I'll be right back.
It's nearly 5 o'clock.
I'm very glad that you're explaining all this, so my own thoughts are put in context. Thank you.
Hi, Carl. Hi, everyone. Sorry for the delay.
Well, yeah. What should we do about this? Because we haven't even started going through answering your questions.
They said so. I live with someone who can hold off the guests.
Well, no. Why don't we schedule another session, and then we can go through go through your particular questions, because they're all, I think, really important questions, and they all will I think, set the roadmap for you and your team for the next few years, and it's important to get them right. I mean, I couldn't resist touching upon them in my stream of consciousness, but it'd be nice just to go back and unpack each one of them, why you should certainly do that, and don't worry about that. That's already been done. How can we do this? Can we nick a methods meeting? In fact, tomorrow's methods meeting at the and for the next couple of weeks, because Peter and everybody has gone to Melbourne for the Organisation of Human Brain Mapping. The 12:30 till 1:30 slot on UK time on Tuesdays is open, so you'll be very welcome to use either tomorrow or the following week.
Tomorrow I'm on a train, but the following week,
well, why don't you now just grab that and then send everybody an invite?
Yes.
With here, and then we can go through the slides.
Just writing a note of this.
Yeah, it's 12:30 UK time, which should be 1:30 your time.
Yeah.
Tuesday, not this week, but next week.
Yes, thank you, Carl, for the time. It's appreciated.
Okay, yeah. Well, you better go and look after your guests.
Yeah, I suppose.
And we put our hands together for a final round of applause.
Thank you. Okay, then I will see you Tuesday next week. And thanks to everyone for coming. And of course, Carl, thank you for the time and the energy you spend in the feedback. It's deeply appreciated.
Will you be sending out this invitation to the TNB email?
Yes, I'll do that.
Okay, great.
And we can probably use the same link and everything.
So the clinical applications questions can be asked then too.
Yeah.
Okay, great. I look forward. It'll give me something to do at 4:30 in the morning. Thank you very much.
Thank you, everyone. Right. Bye.
Bye-bye.
Hello, Andreas. Good to see you again.
Hi, Peter.
It's a pleasure.
Good to see
you. Also, I see Mo has joined the meeting. I don't believe we've met Mo. Nice to meet you.
Hello, good to meet you. I've been in several TNB meetings, but it's been a while.
Perfect. Yeah. And sometimes there are people in the meetings that, as chairs, we don't always, don't always know who's who and so on. So it's just a pleasure to say hi to you properly. I see you're also recording this meeting. Is that right?
Yeah, this is just something that happens automatically with my like it's Read AI. You're welcome to boot that if you prefer the recording that you have. I know that you're going to upload and everything, so.
I don't have a strong opinion. I think we should just make sure that if something comes up in the meeting that for some reason or another means that someone wouldn't want it to be recorded, that I'll ask you to delete the recording or something like that.
Yeah.
I don't think that will happen. I'm the speaker today, and I'm very happy.
Yeah, excellent.
Perfect.
Thank you.
And I expect that you know this, Mo, but this is a continuation from last week's meeting where I presented. So there won't be a presentation today. It will just be a sort of time to round off the discussion from last time.
Yes, perfect. Thank you.
Hi, Carl. Good to see you. I hope the summer is as pleasant in the UK as it is here in Denmark currently. Well, pleasant when you're outside. Currently, it's very hot indoors everywhere. Good. I will just share my screen to make sure you can see it. Can you now see my slides?
Yes.
Saying some. Good. Okay. Okay, then I'll officially bid everyone present welcome to this extra TNV session where we want to finish off the discussion from last week's presentation on the Julia package in ActiveInference, the ActiveInference.jl package. And today I'm again chair and speaker, which is a pleasant, but sometimes socially somewhat awkward situation where, and also because it's an extra meeting today, I think we probably will forgo many of the normal customs of clapping and so on, but we'll see. And I don't know, would you prefer, Carl? I think you said last time that we could go through the slides and focus on the little green question boxes.
Yeah, I think that would be so. Yeah, just treat this as a continuation of the summary and wrap up. This is a longer wrap up than normal. And yes, I think it would be very useful to go through the little green boxes. So if we can just go through the slides, but sort of pausing when you think there was something important said, or actually in retrospect after your last presentation, whether you want to push back on anything that was said or clarify anything. Yeah, I mean, this is for you in terms of staking out the way forward, what you commit to, what you don't commit to. My feedback is really helping you winnow down on things that are going to make a difference, because there's a tendency to be a little bit over-inclusive and a bit exuberant when thinking about having the universal functionality that's going to attract users. Paradoxically, that's not the case. You need to identify who's going to use this, who will really want to use this, and once you've identified that use case, there's only one best way of doing it. You don't want to give people choices. If they have choices, that means you don't know what the best way was, and immediately people will avoid you.
Yeah, they will panic, I suppose, if they're.
Well, yeah, they will literally, in the sense that you've induced a certain kind of epistemic uncertainty, and they will avoid that ambiguity and go to another software package where they don't have to make choices.
Right. Okay. Yeah, also, I just wanted to reiterate one more time, Carl, that this is both very useful and very appreciated that you spend the time in this way. So I've been discussing with my team the feedback from last time, and perhaps not push back, but there's one thing where I wanted to ask about what you said last time. But apart from that, I think primarily some green boxes with clarifications.
Yeah. Well, make sure you don't forget what you want to, what's important to you.
Maybe we should start with that. So it's on this point that you just said that, of course, and and I think that's perhaps already pretty obvious, inclusively natured, in the sense that I easily want to put everything in. I think also as a personality type even. So it's good for me to get some pushback on that. But of course, the idea was, one of the original ideas here was to allow other types of generative models than the POMDPs, discrete POMDPs. And last time, I think you pointed out that most, if not all, use cases, the discrete POMDPs are appropriate, if I understood it right. And so I think, so the plan was, and I think this isn't too hard, to structure the package so that one could, in principle, put in a different generative model and use auto-diff variational inference instead of coordinate descent variational inference or something like this. But not spend much time on supplying alternatives, just so that if some case arose where it was needed, someone could use that, but then focus on the discrete state space kind of from there. And maybe that's what I wanted to ask your opinion on. Do you think, because I have the intuition that being flexible enough to be able to handle that if the need arises is a nice thing. And I don't think it will take too much work, because it's primarily a plug and play structure that most people will use the discrete POMDP surface, which looks like POMDP, and then won't have to worry about whether it's coordinate descent variational inference and what the settings are for that algorithm and so on. They just have to say, I want a discrete POMDP and I want active inference. But for those who would, what do you think?
Well, I think, again, standing back and looking at the use case. So this is not just equipping the community with abilities to solve inference under a generative model, you're doing this to allow people to apply this technology to answer questions about the subject of study, which means you've got this observing the observer. So it's not just a case of identifying the objective, the subjective model, which would be, for example, a POMDP of some economics game or some sort of foraging task. You've also got to nest that in the inversion of the objective model, very much in the spirit of the the hierarchical Gaussian filter, and it's likely that objective model will indeed require continuous state space modeling, and therefore, if you commit to the most robust and generic approach, which is variational Laplace, you will certainly be using gradient descent. Yes, so that there will be a necessary opportunity, or in fact, a necessity for a facility to do gradient descent, not necessarily in the subject's generative model, but in the objective model that makes sense of things like reaction times, which are continuous measures. So yeah, you certainly need that tech. I was, the point I was making there was focused on the use case and why you're introducing that tech, because there are lots and lots of ways of handling continuous state space models, and unlike discrete state space models. So discrete state space models are getting towards the Quinian desert landscape of quantum mechanics and linear operators that can easily be cast in terms of mortal computation. So these are good candidates for how the real things mortal computation works. And if you put too many bells and whistles on, just to add extra flexibility, you're rendering them biologically implausible, and also from the point of view of the free energy principle, deviating from the path of least action, because what in terms of the it from bit and the thermodynamic reading of belief updating, if you don't do it in the most efficient and simplest way possible, you're doing it in the wrong kind of way. So there's an argument to be made that when you're focusing on the subjective model, then if you can't reduce it to an MDP with some product operators, you've got it wrong. However, when it comes to the objective model, you are going to have to move into continuous state spaces and play the same kind of game. So what's the most natural and most efficient way of inverting continuous state space models? And we know that it's effectively an extended Kalman filter. And that, in my world, will be variational Laplace, and that would certainly just be a gradient descent on variational free energy. But there are choices there. You could move then to particle filtering, centered, uncentered filtering, right through to Langevin assisted multi-chain MCMC. You could get into a vast world of other approaches, but in my experience, you don't really need to go there, because if you've got the right generative model, the local second order approximations implicit in variational Laplace should hold, and if they don't, you've got the wrong generative model. So that's a quite a it's a polemic philosophy, but one which has been applied over the past 20 years, 10 years certainly, to dynamic causal modeling, that when your variational Laplace scheme doesn't converge, don't blame the scheme, blame the generative model. And you always learn by a failure of convergence that it is the way that you parameterize the model. You've failed to do an appropriate transformation, or you've failed to lump together certain parameters. That's where the answer is. So in principle, you shouldn't need anything apart from variational Laplace. And I'm being polemic, but if I was your age and I was in charge of a young group, these are if I knew this at your age, it would have been I would have been much less distracted, and people would have wasted much less time.
Yeah.
Sorry, Karen.
No. So I've got the objective, or for the objective generative model, for the inversion of that, I'm relying on this Turing library, which allows exactly so auto differentiation based gradient descent on the free energy, and I think the Laplace, that's the one we just use a multivariate normal, so Gaussian posterior, I assume, right?
Yeah, variational Laplace is operationally defined, and Peter Zietman's got a sort of primer on it. So normally when people talk about variational inversion, particularly of state space models, they normally think you're doing some kind of coordinate descent in the spirit of variational Bayes, where you just iterate through a number of variational steps, while committing to conjugate priors. It means you can actually solve for the minimum. So you solve for the free energy gradients being 0, and that solution means that that is the best solution for this step. But of course, because of the message passing between the factors of the mean field approximation, if you change one, then you change the other. So the minimum moves. So you have to iterate around using conjugate priors. Now, that means you have to write a new scheme for every model. Yeah. And it also means you have to commit to conjugate priors, which in some instances can be an overly restrictive. In fact, in many instances, it's completely inappropriate. So the reason that we did not pursue, after looking at this for several years, next door to the inventors of variational Bayes at the Gatsby Computational Neuroscience unit, people like Beal and Neil and the like, we then invented variational Laplace. So what is variational Laplace? Well, variational Laplace has the same spirit of stepping through variational steps, all the factors of your mean field approximation, your factorization, but not relying upon conjugate priors and just using a gradient descent. So you have usually about 8 to 16 iterations within each step, and then you cycle through the steps. So there are 2 loops. And that is variational Laplace. The other thing that variational Laplace brings to the table is that you transform everything so that it has a Gaussian distribution. Why do you do that? Because of James's maximum entropy principle. So if you've got an efficient encoding of the natural parameters of a conditional density, then the one the one with the greatest entropy with the minimum number of natural parameters, which is 2, mean and precision, is Gaussian distribution. Incidentally, that is also just a second order approximation, the first universally non-vanishing component of a polynomial expansion of any system. So you can either look at this as picking the functional form that defines variational procedures in general of the posterior to be Gaussian in accord with James's maximum entropy principle. Or you can say, no, we're just taking the second order approximation to any nonlinear generative model, where that second order induces a quadratic form to your log likelihoods and log marginal likelihoods, which just is a statement of a Gaussian distribution. So a Gaussian distribution is just, if you like, the simplest approximation to any distribution, if you consider now the log probability expressed as a polynomial expansion of the support. So there are lots of really fundamental savings you get with variational Laplace, things like the sort of conditional precisions, cancelling the gradients, which means you never actually have to explicitly represent the conditional precisions. You just have to optimize the mode or the mean. So the variational Laplace is a very special kind of generalization of variational Bayes that has inbuilt, it leverages everything that can be leveraged in terms of building a maximum efficiency scheme, and from your point of view, rests upon natural gradient descent. And the natural gradient descent is quite important because you know, the gradient descent is informed by the conditional covariance. So although I said you don't need to evaluate or optimize the conditional covariance, there is always an optimum approximate posterior precision if you know the conditional expectation and the posterior expectation. But you do need to actually represent that when you're doing your gradient descent to give you a natural gradient descent. And I think Lance has actually written about variational class doing natural gradient descent.
Okay, I'll make sure to read up on Peter's paper and see if I can find Lance's also, to make sure that this is what I'm doing, or if it's not used. So, and that's what you would suggest for the objective generative model inversion. But
yes, yes. I should just qualify that. I mean, the best paper from my point of view, if you do actually have to equip your POMDP with some continuous interface, is the graphical brain paper, and that explains how you understand variational Laplace when your model has both discrete and continuous parts to it. So it's the same kind of maths. But it just has a different sort of functional form because you're now dealing with continuous as opposed to discrete state spaces, and you have to now, understand the mapping from the discrete continuous to the discrete and vice versa. So this is structurally very different from just equipping like RxInfer every node with the opportunity to be continuous or discrete. So what you now have at hand is a subjective generative model that is at heart, literally, a discrete state space model that has all the advantages of discrete state space modeling in terms of carving nature at its joints. But the outermost, the lowest level is a mapping to a continuous world. So this is a very specific architecture that may be apt for certain subjective models. We don't usually need it because most of the time the observed behavior of your subject is categorical. And even if it's not, it can be made categorical by sort of just binning something, and replacing move to the right with replacing a velocity, continuous velocity, with move to the right, move to the left. But if you want to do that, then I would recommend the graphical brain paper. What you'll also find is, which may not be necessarily relevant for the objective model, is if you want to deploy your continuous state space models in terms of time series, you'll need to work in generalized coordinates of motion. And by that I am subsuming Kalman filtering or Bayesian filtering. So Kalman filtering works with X and X dot. It has implicitly two kinds of hidden states under the hood. One is the state that you're estimating, but implicitly there's also a velocity on that state. So the Kalman filter is the simplest Taylor approximation. It's effectively a first order Taylor approximation to the most general formulation, which would be generalized coordinates of motion.
And so you can add coordinates on top of that. That's a whole different question. I'll ask you some other time. But then maybe my suggestion would be that we make the package so that one could, in principle, add, for example, a model such as the one in the graphical brain or the generalized coordinates of motion, but that the team won't focus on this now, because I think you're right that there may be some cases where it's useful. I have quite a few people asking me if that's something we'll allow. But I think you're right that we should avoid spreading out too thin, and there are more important things to do first.
I mean, the literature that you would need to get into to do the continuous state space modeling is, I repeat, all in generalized course of motion. It is a literature which now is 20 years old from my perspective, applying variational class in the form of dynamic causal modeling. It's a big literature, a big undertaking. It's basically complex system modeling. And if you put action on top, it's very complicated KL control of complex system modeling. And you could spend your entire life in that field. So I think that what you just said is absolutely right. What do you prioritize? And my observation was that you've got something which is unique to your challenge, which is this observing the observer. That's something which you won't find in dynamic causal modeling, and you won't find in any vanilla simulation engine that does dancing, for example. So I appreciate that if you wanted to characterize dancing, you'd be doing complex system modeling, but that is not the agenda of enabling somebody to ask a hypothesis based upon the observations of dancing. So you'd have to have the generative model of the dance, and then you'd have to invert that generative model on the basis of the observables, both of which would be continuous state space models. But the objective model, the subjective model here would be extremely complicated. Not impossible. You just deploy DCM basically. But of course, that deployment would not be active inference. It would just be basically
perceptual.
It would just be this is how the system behaves. This is an n-body problem, and I've now characterized it in terms of its kinematics and the parameters, and it's showing generalized synchrony, and I can measure that and report it. At no point are you using active inference or predictive coding to tell that story. This is purely a description of complex systems. So interesting game, but it's, to my mind, it's taking on too much, which is not quite pointing at what you want to do, which is, assume you've got an ideal Bayesian actor, get some choice behavior, and then ask what are the priors that best explain this actor's choices.
And I think there are some use cases where one might want to do this meta-Bayesian modeling, but where the subjective model uses some kind of subjective state space, for example, where people move together and so on. And I suppose you could use more or less the same models that Connor Hines uses for his fish.
Yes, no, you could certainly do that. And this is a really fascinating and important area of research and actually industry. It is exactly what people are currently looking at in terms of military drone swarms.
Right.
Very prescient at the moment. And yes, you would start with something like Connor's, although you wouldn't actually pursue that particular line of inquiry because his job was to try and sort of rewrite classical Boyd-like formulations of swarm behavior in terms of a very simple kind of merely reflexive predictive coding or active inference. But you're absolutely right. You could get into that field. But you would be a real minnow, a small, very, very small fish in a massive field. So the field is incredibly important, but it's not where you're going to make a difference.
So I will for sure focus on the meta-Bayesian, so having an objective model and inversion that, and I will also focus on discrete state space. But I will make it so that the package could, in principle, by me or someone else, be extended to use a different generative model. We have a plan for this coding-wise. That's not too complicated.
Yes, I mean, I just keep an eye on the importance of being able to make the bottom layer, the interface with the real world, continuous. That's the important bit. So you don't need to equip everything, but just the observation layer. If you could have the choice about making that continuous, then that I think I can't imagine a use case where you need anything else. You certainly don't need to put attractors deep in the model, in the sense that that's already been done. I mean, a transformer architecture is that. So again, you could spend a long time doing that, and then you'll suddenly find that the same functionality has been leveraged in the past 5 years in transformer architectures, and you don't have resources to do that. So
I don't want to compete with the big tech companies at all, right? That's not, yeah, okay. But what if you have, let's say, if the parameters, so this is one use case I've run into, some students of mine who did a project where they wanted to have a generative model where the parameters of the B matrix, in this case, was changing according to a Gaussian random walk, and then inverting this generative model, something like this. That was the only thing I could think of, and I don't know.
Yeah, well, I mean, you can always emulate. I presume that they've grown up with the hierarchical Gaussian filter, which is,
Indeed,
an interesting, visionary, but sort of an interesting little model, because it only deals with precisions and it assumes an autoregressive structure throughout, which is, a simple parameterization, but clearly in the space of all models that you could consider. Not terribly generic. So I think one just has this thing. Well, what would an autoregressive process look like when discretized? It's quite simple. It's just a sort of a probability transition matrix with a certain structure along the leading diagonals, plus or minus one.
Of course, yeah. Yeah, so it wouldn't be hard to discretize this, is what you're saying, and therefore there's no need for a continuous state space inside the hat, as long as the skin of the generative model can be continuous. Okay, thank you, Carl. So this is noted. I think so. That was the most, let's say, pressing thing I just wanted to touch on with you. I have a few green boxes, so if you agree, at least
before you go on though, just come back to how you put an HGF-like look and feel into a POMDP. There is a lawful relationship between this sort of off-diagonal probability transition matrix, which you should write down to understand the math, because it's very simple, and the apparent dwell time and autoregressive coefficient. And one can, if you like, sometimes get away with not actually having, as part of a very deep generative model, this slow switches in a state that, say, maybe generating a precision at a lower level, and instead just use an autoregressive form. So when you actually use an autoregressive form on a continuous variable, that the coefficient, the autoregression coefficients, are basically playing the same role as the precision of a deterministic walk, if you like, versus not moving at all. So if you imagine that the probability transition matrix, which is the identity matrix, means I'm not moving, and then one below the leading diagonal, which means that I am always definitively moving to the next state. And you can imagine mixtures of the two.
Right.
It gives you an autoregressive-like process that can either be characterized in terms of transition probabilities, or it can be parameterized in terms of the precision of these two underlying basis functions, or it can be parameterized as a rate constant, and all of them have the same functional form, basically. So if you just look at sort of the implementation, usually called a forgetting factor. So, for example, in the MDP schemes, to slowly accumulate Dirichlet counts, sometimes we put a forgetting factor in, and that's a shortcut for not modeling a superordinate contextual batch by batch level that has this Markovian slow autoregressive like walk in discrete. So you can still use the HEF formalism even for discrete updates, and interpret the forgetting parameter as, if you like, an autoregressive process. So it does have, it does have an important role to play, but at no point do you necessarily need to invert Gaussian distributions to deploy this.
Yeah, so you would say the forgetting rate in the POMDPs is kind of an approximation heuristic, a shortcut to something you could also model, because that was what the students were trying to do with the HGF, but they're going to be largely equivalent a lot of the time, I imagine.
Yes. And it just encodes how quickly you think the context is changing.
Yeah, exactly. this volatility thing.
Yeah, absolutely. Yeah, sorry. Yeah, so it does exactly come from that literature. Yeah.
Yeah. Yeah, so Chris has updated it a little bit, so you can add drifts and all sorts of stuff to it, but I haven't seen any case where that was necessary yet. So
Well, I mean, in principle, the drift is basically a systematic change in context.
Yeah, exactly.
And then you get to deep temporal models, and
Yeah.
so you'll certainly need it if you did language processing, for example.
Yeah. Okay, that's both interesting and very useful. Thank you. Can I skip to a specific green box that I wanted to ask you about? Just so we make sure we have time for it. Is that okay? Or
Yeah.
do we have, okay. Because it was on the, basically when we were restructuring the package a little bit, and right now we were building the planning part. And a question that came up was, so again, we had the same wish that we wanted to make it so that people could fiddle with it if they wanted to, but there is a strong default that people will most of the time use. And one question here was that I've seen some alternatives to using the expected free energy as the objective, so the thing that's minimized in the action selection or in the planning. So one was the generalized free energy, and that's the one I wanted to ask about. I've seen some others, so I think David Hyland made this path divergence objective, and I've seen that Chris Buckley did this free energy at the expected future objective. And of course, you could also just use the expectation of the variational free energy given your actions, which I read that the the sign of the information gain term is reversed. And so I think what I just wanted to ask you was, is that something you think would maybe be useful or interesting for people to be able to switch out and use different objective versions, even though there's a default of the normal expected free energy? And I realize that I'm not well versed enough myself to fully know exactly how relevant this would be. So some of the papers that present these other objectives, of course, are a bit, they say, oh, the free energy of the expected future is more principled than the normal expected free energy structure, and so on. Yes, does that question make sense?
Yes, it does make sense, and it's a little bit upsetting from my point of view, because if you ask the authors of these papers, they probably want to retract their papers, and certainly notions that one is more principled than the other.
Yes.
So the definitive answer, there's a lot of rubbish being written about the expected free energy. You can ignore all of it. Including some of my early papers. Well, no, that's not true. No, the maths hasn't changed. So it's important that you appreciate this as somebody who doesn't yet know the field, to be extremely skeptical of anybody who thinks there is anything other than the expected free energy as has been consistently defined since its inception and derived in many different ways. The most recent derivation you'll find in the path interval formulation, the free energy principle.
Right.
All of these other ones are variations that break it. And you should absolutely not give people the opportunity to break the expected free energy. Having said that, what you can do is, as Thomas Parr has earned, and first of all, shall I just say, and let me just make it clear, the generalized free energy is just a way of saying that in certain situations, you can combine the variation, you can absorb the expected free energy into the variational free energy to create a generalized free energy. It doesn't mean it's an alternative, it's just another way of formulating it. So you don't need to worry about generalized free energy. All you need to do is to remember that when you're optimizing your approximate posterior over hidden states and acting, then you are minimizing variational free energy. When you are doing optimizing your posterior over policies that reach into the future, you are always optimizing the expected free energy or minimizing the expected free energy. Or selecting the policies with the minimum expected free energy. So there are just two functionals in play. One that is that is an approximate posterior over hidden states, and the other one is an approximate posterior over policies. And they are, because they have different supports, they are very fundamentally different kinds of things. Fundamental in the sense that the variation-free energy is a bound, the expected-free energy is not. It's not a bound. It is a measure of the likelihood that something like you will pursue this path into the future, given the prior preferences or your prior preferences. There's no riddle room. There's no debate. It's just what it is. Having said that, the expected free energy effectively has three terms that cannot be, if you like, further factorized. And that means that you can remove certain terms to get reduced expected free energies in the absence of various kinds of uncertainty. And that allows you, for example, to switch off certain kinds of uncertainty to see what would happen if you had an agent that did not encode or choose what to do under an explicit representation of its confidence or uncertainty about this or that, which is, I think, sometimes very useful. So you'll often find in the sort of RL literature, people have some arbitrary functional forms for their reward function, and they use Bayesian model comparison or AIC to compare this functional form with this functional form, say, oh, this one was the best one, and then write it up. The equivalent here would be basically, for example, using the full expected free energy and then removing the two terms that subtend the accepted information game. So that would be rearranging the three terms into one pair that does the epistemic affordance and the other one that does the instrumental affordance of the kind that people in reinforcement learning like. And then you'd switch off the epistemic affordance or the intrinsic motivation just to see how it would behave in the absence of any exploration. Or you can switch off ambiguity. So that would just leave you with the other pair, the remaining pair, and that pair is what is used in KL control and risk-sensitive control in economics. So you can say, if I was ambiguity unaware and just risk-sensitive, how would I compare with a fully Bayes optimal agent that was both ambiguity and risk-sensitive?
Yeah, you were saying you can basically recover many reinforcement learning, care and control schemes and so on just by turning
Yes, you can. Yes, just by removing one of the three. So it'd be useful just to go in there and just have a switch.
For that,
I mean, yes, you can think about sort of removing one, one or two or three in any combinations, giving you 6 potential reduced kinds of expected free energy, all of which will have some kind of functionality. I think that if it's just the entropy one, if it's just the ambiguity one, I think you get to no, I'm trying to remember. One of them gives you James's maximum entropy principle. Anyway, you can certainly introduce that functionality and then explain what switching on and off different.
May I ask about that? This is
so we only have 15 minutes left, I believe, probably a bit less because Carl has to.
But reinforcement learning, KL control, what are other fields? Because I'm helping to draft a proposal and we're interested in how this could affect others.
I can send you the overview from the book if you want, Andreas, because there's a little overview of how they relate.
Okay, they do that. Then that's answered. Thank you.
Do you agree,
Carl? I think
you've
just listed the basic ones. It's reinforcement learning or accepted utility theory would be the simplest, and that ignores uncertainty about the consequences of action and uncertainty about your states of affairs. And then the next more sophisticated one would be KL control or risk-sensitive control that includes now a probabilistic specification of the consequences of your choices and the outcomes, also known as path integral control. and then you have full active inference where you've got everything in play. It's sometimes easy to understand, as Peter is intimating, if you just look at the three components that come together to make the expected free energy. And for Peter, the definition of a free energy is basically a relative entropy with constraints usually provided by a Lagrange multiplier. So, in the world of describing probability distributions, you start off with the entropy, and then you move to a relative entropy, which is now also, well, for example, a mutual information would be a relative entropy. A KL divergence would be another relative entropy. And then to make a free energy, you add to the relative entropy a cross entropy, and the cross entropy implements the constraints. And a cross entropy is the expected loss function or log likelihood function probability expected under another density. So the cross is, and that's usually the expected utility is a cross entropy. So just the nomenclature from the the sort of the information theory or the physics is a free energy has to have three terms. It has to have two bits that give you your relative entropy, and then another bit which gives you the cross entropy, which is what I was
constrains
saying.
it.
So if you understand what those three terms are, you can now look at all kinds of reduced expected free energies. And as Andreas was pointing out, they have clear correlates in the in the control literature and economics literature and in the behavior reinforcement literature.
Yeah. Okay. Thank you. And I think, do we have time for one more question, Carl?
Yes. Yeah. Inductive inference is very important. And if I were you, I'd focus more on that and less on sophisticated inference, because if you've got inductive inference in play, you can reach a long way into the future. Whereas if you've only got sophisticated inference, then you're limited in how far into the future you can get. And of course, you don't need, I said this last week, but I'll say it again because I think it's important. Sophisticated inference deals with uncertainty in a very sophisticated way. The problem with appealing to and only to sophisticated inference is that, of course, uncertainty accrues as you move further away from the present, which means there's no point in doing deep tree searches properly. There's just no point in going so far into the future. You have no idea what's going to happen. So the whole notion of deep tree searches is a bit stupid. It only makes sense when you've got very precise beliefs about the transitions.
When you can expect what will happen very precisely, then you can plan it.
And that's inductive inference. So you make sure you've got both sophisticated and inductive inference. And don't worry about the early literature where the frame of reference of the policies is fixed in time. That's a distraction. It was developed specifically to look at sort of dopamine. Let the policy move into the future from the present. It makes things much, much simpler for you.
So that's the gamma and these things that we shouldn't.
That's correct. You can still recover gamma. You can still recover in fact, the gamma, the expected precision of your beliefs about policies is just the average of the expected free energy, which itself scores the negentropy of your beliefs about your policies. So heuristically, it is just the average confidence you have in what to do next. So you can derive gamma analytically from the posterior over policies that just as a softmax function of expected free energy. You don't need to balance it with evidence that you're pursuing this policy or that policy. That only gets into the game when your policy doesn't move with time. This is the thing that I do on the third move of this game. And now I realize I'm not pursuing that policy because what I did last time is not one that can't be this policy. You don't need to worry about that. Just real things will just say, okay, I can do this, this, and this now. This has happened to me so far. What do I do next?
Okay. Is there a good place? Because I think we've the original version of the package was based a little bit on these older formulations, I think.
Yes, I noticed that. Yes, yeah. You want to declutter that.
So where do I
Decluttered.
look? Where do I look for a decluttered version that I can rebuild it around?
Well, most of the more recent descriptions of active inference will show you that. I just
Thomas's
go
book.
to. I'm not sure actually. I mean, because Thomas was writing that when he was still a PhD student at UCL. I'd go to one of the more recent descriptions of discrete renormalizing or universal MDPs or generalized MDPs, where there's a big table that writes down all the update equations, and that's more isomorphic with the actual SPM code. So you need to get access to the current implementation of the. So in the SPM MATLAB code, there are 3 generations of active inference. You've been working with first generation code. So there's 0. Right. There's SPM underscore MDP full stop .m. That was the very original code used to write those original papers and introduce the idea. And then we introduced X, which actually had a factorization, allowed for factorizations. That was the first generation. Then there was triple X with the second generation, and now we're on, double X, and now we're on triple X. And triple X doesn't have inside any of the gradient descent anymore. It's much simpler. It does effectively belief propagation as opposed to gradient descent or variational class, as it were. Well, it doesn't do a gradient descent because it doesn't need to. The math is sufficiently simple. You can just jump to the best, the best inference
with a single equation.
With a single jump. Within each of the factors of the unknowns, you can recover what you would have got had you done a gradient descent to generate ERPs and things. And if you switch that neural, it's called it's a flag called neural or capital N. You can switch it on and it will generate for you what you would have got had you done a full gradient descent. But the actual implementation is much simpler. When I say simpler, it's much more involved, but it has been refactored to be in little modules. But the third generation MDP code has come a long way since the writing of the Active Inference book, and in many senses it's now much simpler. It just looks a lot more complicated because it's now got a lot more functionality. It's got some, and you'll find if you actually look at the code, to your horror, you'll find that not only are there latent states, but there are also latent edges. So you can now actually move edges around and plug in factors to different likelihoods. And there's lots of functionality in there. But what it doesn't have is a sort of the gamma and
that's all fine.
Like
the gamma. I think we only did it like that because that was what we had at the time. But I think I should have a look at the third generation MATLAB code.
Yes, no, absolutely, and it only uses sophisticated inference. There is no other inference once you've discovered sophisticated inference, and it does it with a self-recursive calling routine, which is as efficient as you can get. And people have tried to emulate that. I think Paul Ashwin tried to emulate that and got it wrong. So again, be careful. Young people trying to understand what's going on here, understand years, if not decades of man-years, if not decades of work. But sometimes take shortcuts that are just wrong, and they get it published.
Because a reviewer won't necessarily notice, I suppose.
Oh well, sometimes they do notice because it's usually me, but I have to balance the I have to balance the interests of the PhD student and building their CV with the veracity of what they're putting into the literature. But I have to do a lot of damage limitation post hoc because of this. But it's just part of the learning experience.
So perhaps I should have a look. Maybe we should make that. Do you know the PymdP implementation? is kind of corresponding to the third generation now?
It's
or not?
getting closer, but it's not got everything. So you ask John. John's probably the person who knows the relative functionality. Yeah, the PyMDP has the beauty of the SPM simplicity in terms of refactoring and modularizing the code.
We've factorized. John has factorized the Julia implementation, so that helps.
Right.
I guess that gets us to generation 1 or 2 or something, but not all the way up to 3.
I don't know because I've only ever worked with the MATLAB code.
Hmm.
No, PyMDP doesn't have. I don't think it has sophisticated inference, but it does have learning, whereas I don't think yours has learning yet. So there's lots of.
We have parameter learning. We don't have
Oh,
structured
okay.
learning.
Oh,
And
right.
we have sophisticated inference now due to John implementing that, and inductive inference is next on the to-do list, so to speak.
Right.
But I think it has some legacy things. For example, we also have the forgetting rate, learning rate stuff, and the gammas and stuff. So things there that we might want to throw away.
Well, I mean, the triple X or third generation MATLAB codes still has that forgetting for the learning. And just for your interest, you mentioned the average of the expected free energy. In fact, you didn't. You mentioned the average of the variational free energy, but in fact, the average of the expected free energy just as a mutual information, and that also gets into learning because you can update when and only when the expected free energy, which is the mutual information, increases. So that and you'll find that described more clearly in these more recent descriptions of the scheme. So
I might, with your permission, write you an email just for a link to one of these, because I was Googling a little bit, but I would rather write
right,
papers.
okay. Do from pixels to planning and
Okay.
see if you get either a Frontiers or Entropy paper.
I am. I know this. I haven't read it in detail, but I know the paper. Okay.
Okay, if you just scroll down a little bit, you'll get all the basic structure. I'd say you're going to need to look at the code to
understand or know exactly how to do it, of course.
So that's the structure of the generative model, and you can see it's got one formulation of expected free energy here. And you'll notice, for example, there are lots of sort of simplifications and generalizations, so that the E-tensor, which used to encode habits, is now informed by the level above. So it's now conditional. So you can infer the context in which your habit will emerge, and then it's supplemented with the expected free energy, which is G. But if you scroll down a bit, the actual functional form of the updates go down. Oh, must have missed the figure 2. Oh, here we are. Yeah. So there are all the updates you might possibly need. And then if you look at the next few pages, there were 3 sections entitled Active Inference. Active, that includes the planning.
Learning.
Active learning, which is the updates of the learning, and then active selection. So it just sort of tries to link everything together as the 3 different kinds of updates.
That's very good.
I say that you won't be able to reconstruct that in Julia. You'll have to update your current code in relation to the MATLAB implementation.
Exactly. Yeah, so I think we should take the MATLAB implementation as our starting point, basically.
Yeah.
For the updates here. So then a very final question. I expect it to be a yes/no question. When in sophisticated inference, when planning my own belief or imagining my own belief updates in the future, should we also include parameter learning there? So do I imagine my own parameter learning in the future? And we can make it optional, was what I kind of had planned, but depending on your answer, of course.
I don't think that's been implemented in the MATLAB version, but I do recall Ryan Smith and one of his colleagues incorporating that. It's not something that that has been a thing from my perspective. You certainly have the novelty term. You still got the information gain about parameters, but not the beliefs about parameters.
Yeah.
I haven't really thought about that because, of course, resolving epistemic uncertainty in relation to the parameters, that's an unusual. I usually think about this as basically, do I look behind this door in order to
guess you could take actions where you would learn a lot about the parameters, which would mean that you would then know that you should do this and not that, or something like that.
Yeah, yes, it may well be a little bit too far, because if you change your beliefs about the parameters, you're also now changing your posterior predicted densities over the states, which means that in principle, you could be looking at quite a vast search space, and I don't know. It's not something which for me is of prime importance at the moment. It'll be about, it is at the moment quite sufficient just to choose those actions that are going to resolve uncertainty about my parameters. And I know that I will have a more precise belief if I pursue this kind of action, and therefore I know I'm going to be able to plan more efficiently under those beliefs, knowing particularly what my precise beliefs are about may or may not be useful in terms of future planning. But my suspicion is the computational complexity
explodes
too
quickly.
Yeah, and as such, that would mean at some level you're compromising the marginal likelihood or the free energy. So remember, there's a tight relationship between the statistical efficiency and the thermodynamic efficiency, which translates on von Neumann architectures to floating point operators and reading to and from memory. So you want to try and keep that as small as possible, otherwise you're using implicitly the wrong kind of generative model. And my suspicion is that incorporating counterfactual beliefs about parameters conditioned upon doing this or that above and beyond just the information gain about those parameters, that would only have a difference in terms of planning, is probably not. But read Ryan's paper and see what you make of it, see whether he was able to show a difference between the two kinds of schemes.
And I mean, I think implementation wise, it would be easy for us to allow both, and then maybe not include it as a default. I think it would be easy. That's my claim now. So maybe if it turns out to be easy, we'll make a button that you can activate to do it and leave that off by default.
Right.
I would say. Yeah. Thank you, Carl. So I realized that the next meeting is about to start, if I'm not mistaken, or is it? No, that's later. Yeah. How is your time backend?
I'm fine.
Okay, good. Now I don't want to eat more of the time than necessary. Then I might take the freedom to ask you one or two more things. But these are the most important ones we've touched on, I think. And I hope that you wouldn't mind if I, in the future, when we've worked some more with this, maybe return to a TNB meeting like this, and so that we can check with you whether we get it right or not. Because I should say, it's easy to get something wrong somewhere, and I would want to avoid that, essentially. So
right.
I hope you don't feel you're wasting your time.
No, not at all.
Good. Okay. Then let me just see if I didn't have, one point more that I would be happy to touch on. So amortized inference just means using some machine learning technique like deep learning to as a shortcut to give you the posterior when the model is too complicated. Good.
Yeah. So some people call that deep active inference. So it's just, if you like, either replacing some variational message passing with a neural network, or you can look at this as actually parameterizing an approximate posterior with the parameters of a neural network.
Yeah. So we'll I think we can allow that too, somewhat easily.
You
but
can
not
allow
focus
it,
too much.
but again, if it takes time, then I wouldn't do that. Simply because you have to ask yourself, why would you want to amortize?
Yeah, it seems like a hacky solution to me.
Well,
Like,
well, it is a hacky solution, but it has a purpose, and I'm asking you, do you know what the purpose is?
I had it presented mostly as if the computational complexity is too large, because, for example, you have a generative model with a lot of factors, and so having a pre-trained deep neural network do it for you saves time, essentially. But
Yeah,
there might be
I
better
think it's
reasons.
the saving of time.
Yeah.
So if you've learned everything you can learn about some likelihood mapping, for example, or prior over state transitions, say an A or a B matrix, and you know it's not going to change, so there's zero volatility, then you can incarcerate that knowledge in a neural network. And that gives you a direct and efficient mapping from the data, for example, directly to the approximate posterior in question, if it's, say, the likelihood, or it gives you a fast and efficient mapping from the posterior over the states at this point in time to the states at the next point in time, without having to worry about sort of either coordinate descent or gradient descent on the variation for energy.
Could it even jump straight to the policy posterior, for example?
No. People keep trying to do this, and indeed I've reviewed already 2 abstracts for the International Workshop on Active Inference, and people trying to do this. It's certainly possible to cherry pick some of the time invariant terms from the expected free energy, but notice to amortize is to assume that this is time invariant.
Yeah.
Which means that it has to be state invariant and context invariant. So as soon as anything's conditioned upon a state or time, such as your beliefs during foraging, you can't amortize. So it has a limited role when you're absolutely sure there's nothing more to be learned, and that what is to be learned will never change ever again. So you can see immediately that certain kinds of likelihood mappings would be candidates for amortization if you wanted an efficient scheme. But the reason I say don't worry about that is that your use case is not autonomous vehicles. It's not creating an efficient expert or specialist that efficiently does Bayesian inversion. Your use case is enabling scientists and others to make inferences about a subject, and of course that subject will bring their own likelihoods and priors to the table that you may or may not want to amortize. There's very little point spending a lot of time and money and memory on training a neural network to replace the likelihood when you can compute it almost instantaneously with standard belief propagation.
I think you're right.
If you were building something that was not context sensitive, such as an autonomous vehicle in a very well controlled environment, then yes, you'd worry about amortization. But if you're not, then don't worry about it.
Noted. Okay, then this is a minor thing, but I was trying to make a sense of the field, I think, and made this little splitting into the papers that do, I call it theoretical modeling, but essentially these simulations to show that, attention can be implemented like this as active inference and so on, so where you don't fit it to data. And then there are the machine learning people like Versus and John Boyk, etc., who want autonomous vehicles or whatever. And then the category I fall into, which I hear called applied cognitive modeling, but the meta Bayesian, when you have an objective and a subjective generative model, etc.
Yes. Yes.
Do you think this is a reasonable way to split
Oh,
it?
absolutely. And this is exactly the distinction that I was just referring to. You're not treading on the toes of things like versus and a vast other number, and indeed even versus in its brief as a cognitive computing company is not at this stage so interested in modeling the cognitive computers that it's trying to equip the community with. So I think the notion of applied cognitive modeling is exactly your niche area. And well, you can discuss it with John, who's clearly representing versus. And in the future there may well be a synergy between the work that you're doing and now characterizing the cognitive artifacts that companies like Versus are creating using applied cognitive modeling. Yeah.
So if John would, of course, so he's helping us because he would like to work in Julia, and it has some advantages for readability and so on. That's a whole different discussion where I don't have very strong opinions, except that specifically for applied cognitive modeling, it's very useful that Julia is auto-differentiable, so that you can do gradient descent when you fit models and so on.
Yeah.
But at least one thing we wanted, and then now you may tell me that that's a bad thing to want, was to make a tool that could kind of accommodate all three use cases. So starting from the cognitive modeling and theoretical modeling. But since John has joined, having at least in the mind that it would be nice to be able to use it for machine learning, I think. And I don't know. So I'm not going to bother spending any time on thinking about how this code would be implemented in a specific robot or something like that. But for example, I think the machine learning world wants things to be fast, and they want them to be able to solve difficult tasks efficiently. And the goals are somewhat different. Yeah, so essentially, yeah. Do you think that's naive to think that the tool we make could, at least in principle, be useful all three places, even if we focus on the last one? And it's a bit of how we market it, right? Do we say this is a tool only for applied cognitive modeling, or do we say
Oh, I see. Right.
this is a tool that can do all three?
No, I mean, you'd certainly have to be able to do the theoretical modeling to find the right kind of generative model, which will be the subject's generative model, before you can do your applied cognitive modeling. So you're certainly going to have to have the best equipment around, or as good as anything else, to do the theoretical modeling before you can actually now use that as an observation model for your subject's behavior. The question about machine learning is a bit more. It's a little bit more vexed. It's just, if you're talking about machine learning, then that sort of precludes inference. The whole point of this is based on active inference. It doesn't do what machine learning does. Machines learning can learn to infer, but again, in a context and sensitive way. So, yeah, right, okay. And then it begs the question of, what are these purposes? And then you're into a world where you will have competitors, both sort of morally and financially. You start saying, oh, look, we can use our tech to do autonomous vehicles or cognitive computing in this context, or swarm do swarming in drones. Then you are in a much bigger marketplace. And you'll have competitors. And I think you're possibly even wandering away, well, perhaps you want to, from science and academia.
Personally, that's not my aspiration to wander away from, at least not currently. We'll see when there's a job offer with thrice my salary, but at least I prefer, let's say, this space. That's also where I've grown up and where I intend to stay. That's why I'm going to the ETH in the Klaas Stefans group now, right? They're working here. But because I think the main reason for my part to make the tool able to do all three is that if someone develops something in one, it's also available in the others. So if someone, if someone, someone like John who wants to use it for engineering purposes, implements inductive inference, then now it's also here. So we don't have to implement everything multiple times.
Yeah, but I think your job is to pick out the bare essentials that will include inductive inference.
Yeah.
The engineering purposes, that's an application of this tech, and the more specialized you go and the more applied it is, the less generic and useful it will be for academic research or clinical research or market research. So
so it should never be at the cost of the actual research, cognitive research or neuroscience research, I would say.
Yes, yeah. Yeah. I mean, you decide. It's just that in terms of applying it to people, it means that the generative model that does the theoretical modeling of people has to be biomimetic. And the applied cognitive model, if you're applying it to people, then you're going to have to be biomimetic. If you go into engineering, you're no longer biomimetic, and that means that you are trying to sell a product where you can apply cognitive modeling to drones. Why would you do that? What are you going to learn? You've already written down the prize. What are you going to learn?
Yeah, exactly. Yeah, so maybe there might be cases. John had one idea where you can do kind of cognitive modeling of users using some tool you've designed.
Yeah,
or something like
but
that.
the user is a person.
Yeah, exactly. So biomimetic again.
Yeah. So as long as you get the right biomimetic, the right first principles, which you will need for the theoretical modeling and the applied cognitive modeling to the theoretical models or subjective models, you'd be fine. I wouldn't worry about the engineering aspect. I mean, that's the engineering is I've got a particular use case and I'm just going to use what works.
Yeah. Okay. Agreed. So I won't stop someone from John working with the package if he thinks he can use it for that kind of tools, but I won't prioritize it, and I for sure won't compromise the primary goal, which is the applied cognitive modeling and the theoretical modeling. Then. Okay, almost there. Yes, we discussed the structure a little bit, so I anticipate that I may want to rethink it once I've had a proper look at the third generation implementation. Because this is a structure that we were trying to essentially factorize or and also get an overview of the implementations we've been working with, but that's by now perhaps outdated. But yes, but I just wanted to touch on it. We discussed it a little bit last time. So at least in this 0 or first generation version we have, that's the generative model. We do belief updates, which includes state inference, learning, could in principle include structure learning also. And I've called it prediction. That's just the calculation of the expected states in the future given some actions. And the reason I split it like this is because the at least traditional sophisticated inference loop that goes through the future will essentially run these two functions. So it will run the belief update in the future, and it will run the expectation over states and observations in the future, kind of intermittently. And originally what I was thinking was that if you have a different generative model and therefore have a different belief update and prediction function, they could essentially just be plugged into your sophisticated inference loop modularly without so that we can reuse this part and so on. So the aim was to split it up so that we can reuse components of it. And last time you pointed out that the classic kind of structurings, either in terms of how slowly things change. So here I've sort of state, action planning, parameter learning, and structure learning. And also, of course, there's other structuring in subjective and objective generative models. That however we frame our active inference model should be within these framings, and that I agree with. So I just wanted to touch on this, do you think in the third generation implementations that this is still somewhat sensible, that you could, in your sophisticated inference loop in the future, essentially plug in some belief update and prediction functions that are appropriate given your generative model? Or do you think that that's going to have to fall apart? I don't know if that question makes sense.
I wouldn't distinguish between some different generations of active inference and discrete state models. That this level, coarse-grained level of intuition should apply to all of them.
Okay.
I have to confess, I don't quite understand this. If you put planning as opposed to prediction, and then action selection from your plans, I would have understood that. But
Right.
certainly you can't put sophisticated inference in action. Because the sophisticated inference
Right.
requires
Yes.
belief updating under a generative model. So there's no difference between belief. Mathematically, there is a difference between belief updating when you're updating your beliefs about states, and that's to minimize the variational free energy, and then you use the products of that belief updating to update your beliefs about policies, and that's the planning. But the planning depends upon the belief updates about the states. Replace prediction with planning.
Planning. Yeah, so, and I realized just when you said it now, I'm sorry that I was using the terms imprecisely relative to how they're used normally. I suppose action is after you have your posterior over policies, you just select the action for the next time step.
That's correct. And interestingly, that can have a lot more machinery, which is beyond actual inference. So normally in active inference, both for discrete and continuous state space models, action just minimizes proprioceptive or actuator prediction errors. That's the only thing. It can only change the variational free energy by changing the data, which means it can only change the accuracy of the data, which means that's the same as minimizing the prediction errors on the reports of the data that can be changed by action. So that's action in terms of active inference can be separated from belief updating and planning, and would be a separate module. So even when you use sophisticated inference and you're constrained by inductive inference, all you get from this is a probability distribution over the policy, which includes a probability distribution over the next state of the world, and then that produces predictions about what you should actually sense, and then action itself minimizes free energy by rendering those by changing the state of the world to produce data that are closer to your predictions.
Yes. Yeah, but because I think what we've normally done is just to marginalize the posterior over policies to get the posterior over the next action.
Right, that was certainly in sort of first and second and third generation, but now there's an opportunity in the third generation to say, and this is I think expressed in terms of the difference between explicit and implicit action.
Okay.
So if you switch on explicit action, it will select the action according to the known generative process. So this is all outside your brain. It's your reflexes, your IMU, your actuators that works out what action should I take to make my sensations as close as possible to the predictions. And again, you're minimizing a KL divergence to do this, but it's a KL divergence that is the thing that minimizes the free energy. If you don't specify that explicit action, then you just pick the most likely action from the beliefs about policies and assume, and then give that to the environment, to the generative process, and see what happens. So you've got a switch here, and when it comes to simulating real world engagement, you normally want to do the explicit action, where the action would be separate from the planning.
Yes. So the marginalization is an implicit action that just kind of says, I think this is what I'm going to do as the next step. Okay, good. And this is something I can see probably in the pixels and particles paper
Yes, it's certainly mentioned, but not. It's only mentioned briefly, but certainly it's an important distinction. And you should have the you should include both options for people.
Yeah. Good. Okay.
In the context of sort of economic games, you don't really need to have to model which button is being pressed. You can just assume that the subject's always going to, or you can sample from the posterior over predicted actions to actually model the actual action that the subject prosecuted, even with the shaky hand parameter. But if you wanted to actually put this into a drone or an autonomous vehicle, you couldn't do that. Because it wouldn't be robust enough. You'd need to set the end point or the fixed point of the next move, as opposed to supplying the movement that would hopefully take you to that fixed point. So in practice, depending upon the use case, you may want the explicit action functionality.
Okay, that's very good to know. And I'm sure I can find that in the MATLAB code.
Yes, but just look for explicit and implicit action, and you'll see how
that's an important part. Okay, that's very good to know. And I had in this figure that I had before, I had split apart updating beliefs about the current state of the environment and calculating the expected states of the environment given an action when I'm planning. The second of those two, is that what we call planning specifically? Because I had thought of it as a component of planning, that planning was doing that many times in the future and seeing what happens.
Oh, I'm just using planning to evaluate your posterior over your policies. That is just the evaluation of the expected free energy. That just is the application of in the current generation, the joint application of inductive inference, if so specified, and sophisticated inference.
Good. Okay. So then calculating the expected states, would you call that a part of the belief updating or something else?
The expected states, the latent states.
I suppose it's called the predictive posterior also. Don't we do this, that we say, given this action, I expect?
Oh, yeah, that's called the posterior the predicted posterior. Yes, and you start. Yes, that's absolutely right. Which is why I'm saying that.
So what would
you use the predicted posterior to evaluate the expected free energy, and that's why you call it expected.
Yeah, exactly. So what if we don't have to spend too much time on this, but I think it's good that I'm using the terms in the right way when I'm showcasing and so on these tools, and so that's why it's something like this, perhaps, that calculating the predictive posterior is part of the planning, and once you have that, you can have an action module in the end.
Yes, you could. Yeah.
Good. Okay. I'll and maybe next time you see this, if you notice I've done something wrong, I'll just change it. But for now, I'll kind of conceptually, at an intuitive level, and also I think if it's useful at an implementational level, structure the package like this. So I hope I'm explicit that this is very useful. Yes. Good. Is this the very last one? These ones I asked already. Yes. So very last question, if you're not, if you don't want a break. And this is maybe a stupid question, so I hope you can forgive me for that. So Q, meaning the approximate posterior, just the posterior, also the belief about the states of the environment, I usually think of as not part of the generative model, but part of my inference process about the generative model. But priors, I have at least been told often that priors are part of the generative model. But of course, my belief at one time step is my prior at the next. At least that's how I'm used to thinking about it. And so now I'm asking so that I can have it cleaned if I'm thinking about this in the wrong way. But in that case, I have had some confusion about, at least terminologically, whether to place the priors. So whether to distinguish priors from beliefs, given that beliefs are, of course, so the belief is the posterior and the posterior is the prior in the next time step. Whether to distinguish the two and where in this diagram to place them. Now the old diagram is here, but should they essentially be placed in the generative model or in the belief updating? Does that question make sense?
Yeah, so the terminology here is quite straightforward. The generative model is just a probabilistic specification over everything, sort of joint latent states and the observable consequences of those states, that is usually split into or factorized into a likelihood and a prior. So all the priors go in the generative model. And you're right to note that there's a distinction between the prior preferences that underwrite the evaluation of the expected free energy and the empirical priors that result from Bayesian belief updating. So that's often a source of confusion, that the priors over latent states in updating your beliefs about latent states under the belief update part of your box are not necessarily the usually time invariant priors that specify your preferences for preferred outcomes. So make it clear what they're being conditioned upon. And in the paper that planning from pixels to planning paper, that's made explicit by having the prior over outcomes conditioned upon different things. It can either be conditioned upon C, which are your prior preferences, or it can be conditioned upon the past, in which case I can't quite remember now, but it might be time. Well, you'll see that the priors, the use of the word prior can apply to different probability distributions. Beliefs always have to be qualified as Bayesian beliefs. And if you say Bayesian beliefs, you're normally implying a posterior distribution. And the posterior distribution is a consequence of belief updating. So the Bayesian belief should go in the belief updating part.
And does the Bayesian belief not supply the empirical prior at the next time step, or am I confused in this?
Well, you could certainly look at it like that, yeah.
But they're still, let's say, separate entities belonging in different places.
Yeah, I mean, they're just different words for different probability distributions. But empirical priors are usually refer to deep models or hierarchical models that come from a next scale. But yes, technically, you could certainly look at belief updating as empirical priors from the past, so using a temporal hierarchy as opposed to a deep structural hierarchy, and that's certainly one classical way of looking at belief updating. It's basically using yesterday's posteriors as today's priors.
That's how I've been taught.
Yeah, it's not normally, though, in the context of filtering, you wouldn't actually use that terminology, because when you start to run forwards and backwards in time, it's not quite clear then whether, if you've run forwards and then backwards in backwards algorithms, then it's not quite so clear that updating your prior twice or possibly three times licenses it to be an empirical prior. So normally in time series models, you reserve the notion of priors, and in particularly empirical priors, for something that is inherited from above. It can be still conditioned upon things, but it's not dependent upon the same states at different points in time.
So something like an initial belief or a starting belief. I'm also thinking of course, of the D matrix here in a simple.
So that's an ambiguously a prior, because it's never going to be updated.
Yeah, and of course you kind of, so to speak, replace the initial belief with your Bayesian belief, updated Bayesian belief, once you've received the first input in these time series things. Right?
Yes, and that would be backwards message passing, which actually is not necessarily part of the third generation. You can switch it on, but it's a bit computationally expensive. So you can post date your posterior over the initial state. So I can change my mind about what things were like at the beginning. But that's not the prior. That's now a posterior.
Yeah, over the same thing, right? Yeah, that makes sense.
Yeah,
so postdiction is also something I think that could be relevant in kind of memory research, of course, but not something I've touched on. But so I think we would want to, at least long-term, allow that to have postdiction things where you can you have people do some experiment, ask them what happened, I suppose, or make them report what happened, and anticipate that should essentially their report of what happened should be a postdiction back in time. That's, I suppose, old news. Okay.
Yeah, if you want to do postdiction, then you won't be able to use belief propagation. You'll have to recourse to iterative variational message passing,
Okay.
which is fine. But you'll find in the third generation code that